It's going all right. It's no longer on the shelf. It's a step forward. Yeah, we just had quite a while to film a molecular source for it. So that's done. Yeah, so it's in the vacuum. We have molecules going through it. Okay. That relates a lot. You have lasers on we have the lasers, but they're all using it. So we have to improvise a bit. I guess we'd originally thought actually, it's not to work out, right? No, they're not diodes. Don't use diodes.
Independent of the absolute mass. Now, depending on the mass, this has
Well, we'll see. Yeah, masochist, maybe that's it. It's not beautiful to do.
And this sense of mass is traveling into the vortex. The particles again does matter.
So there's a little bit of work to do still.
This particle moves towards it.
Hopeful.
And the other not.
It'll be a useful method.
You can calculate based on the conservation of energy and angular momentum is that basically all the particles after the collision they will fly closer. For this particle V1, mass 1, before the collision has this vector in the sense of mass 2. After the collision it's an elastic movement. The length of this energy is an elastic scale. That means this particle needs to be solid.
Your molecule looks very happy there. It's a happy molecule. It's a happy molecule.
Yeah.
I like it, yeah. I'm happy to be there.
And this you can find. Otherwise, it's all centered around the world. No, this.
Very nice talk. I love the intersection so much.
Well, it's not that's a great
Yeah,
Should we start? There are a few people arriving from the lab too still, so
I don't mind if you start later, but please don't cut me then.
I don't cut the problem. Okay, I think we start. For those of you who don't know me, I'm Stefan Tucker. I'm now at the Fritz Haber Institute. I'm in chair for this afternoon session. And our first speaker is from Munich, Jan Rempe. And he's going to tell us about this really cool collision experiment with polyatomic molecules. So please enjoy. Floor is yours.
Okay, it's my turn. Can you hear me? Is it on? I have no idea. It's on, okay, thanks. Okay, like everyone else, I would like to join the crowd and thank the organizers for bringing us together here. It's a wonderful place. It's a wonderful meeting. Thanks for the occasion to let me speak here. Not only me, but Martin will also speak tomorrow afternoon or so. So we have 2 talks from our group. It's kind of annoying. Anyway, so this is about cold collision experiments with polyatomic molecules. And the more we do actually about these experiments, the further we dwell into the physics of it, the more fun it makes, I should say. Of course, there are the usual ups and downs, and sometimes things don't work, but in general, I would say we are pretty happy of the progress that we made over the last years. I will comment a little bit about this. So where are we going? So this is kind of introductory slide. I really don't have to show it to you to some extent, but of course everyone enjoys, so to say, the first slides. It should be kind of very general. This is very general. So there's basically 3 requirements that we would like to meet in cold molecule experiments. Of course, one is that we are cold. Okay, the molecule should be cold, but in the end they should also be slow in order to trap them. And the third requirement would be that they should be dense, because in the end we want to make collision experiments. So 3 requirements are necessary: cold, slow, and dense, just basically for the purpose of doing something like this, forbidden by the police, but allowed by molecules. Okay, and that's basically where the fun is. Meeting these 3 requirements is kind of not so obvious how to achieve this. At least when I go back a little bit, some years, it wasn't clear how to make polyatomic molecules cold. It wasn't clear how to slow them. Well, slowing this maybe was the most easy thing, because the Stark decelerator was invented already something like 20 years ago. But we are not using a Stark decelerator, as I will explain. But to make them dense and the kind of collisions that one could see, is basically not very well known. So there are big question marks here. If I go back some years, so how far do I want to go back? Well, yesterday in Ed Narevicius' talk, we heard that he went back something like 10 years and told you about the progress that he made in 10 years. So I would like to go back 15 years. 15 years, we were in this room. Okay? Maybe some of you remember, we were in this room. It was my first meeting which I attended. First cold molecule meeting, of course. Excuse me? It was 2004. It was the first week of January in 2004, and it was not only a cool meeting, it was also a very cold meeting. Why was it cold? Well, the first week of January, as I said, it was very cold outside, and they turned off the heating system in this room because there were holidays, the New Year's holidays, basically. So as you can see, we were all standing and sitting there with big jackets on and caps on top and gloves and so on. This is not just a fake picture. This is how we were sitting here during these, I don't know, 2 or 3 or 4 days, I don't remember exactly. So that was really fun. And I raised this question, basically, how to cool and make dense and how to slow down, basically, polyatomic molecules. And in the end, this is our approach that was basically built on the experience that we gained after this. And one of the essential requirements is that we are guiding the molecules, we are keeping them trapped, if you like, in 2-dimensional or 3-dimensional guides. And we don't want to let them go. So once we have a molecule at hand, we don't want to let it go. So keep it. Never let it free. That's basically the idea. So the molecule comes out of a bottle. It's a very simple experiment to some extent. It comes out of a bottle. It's chemically stable. That's what makes it nice. It comes out of a bottle. It goes into a cryogenic system. We learned a lot from John Doyle's group about how to build and design such a system. So it's cooled down with buffer gas, helium buffer gas, neon buffer gas, something like this. And then, because the molecule, as I will explain, are too fast, we decelerate them. We developed a decelerator. It's a centrifuge, kind of centrifuge decelerator, which I will mention very briefly. And then, in the end, we put it into an electric trap. And this is basically the outline of my talk. So I will start with a gas bottle, more or less, and then walk you all the way through this. But let me just emphasize a little bit that this electric trap is really something which works very, very well, because it can cool. You can cool in this trap. I will not explain the cooling, but I will just show you 1 or 2 slides of basically how this trap is operated. There's some source, it could be a room temperature source, as I said, a bottle. Molecules coming out and they're guided. There's these sharp bends in the guide which serve as velocity filters, and the molecules just arrive in the trap. We can load the trap with molecules. There's a little entrance hole, there's a little exit hole here, and the molecules just accumulate in the trap. We can irradiate them with suitable laser light on a vibrational transition, in this case, irradiated with microwave fields, with radio frequency fields in order to implement a Sisyphus cooling scheme, which, as I said, I don't want to go into the details. But let me emphasize, it's really as simple as this. There's no cryogenics or so involved. There's no deceleration involved. It's just a connection, a DC guide, continuous electrostatic guide. It's only filtering of low field seeking molecules. And this sample can be cooled, and this is already going back to 2016, something like. It represents an experiment where we trapped about 300,000 ultra-cold formaldehyde molecules, in this case, H2CO, formaldehyde molecules, and this shows the integrated energy distribution. So basically we are taking a radio frequency knife, we are cutting into the sample, and we are cutting away the molecules. And depending on where we cut the molecules away, at what kind of temperature, that of course determines the temperature of the sample. In this case, it's about 420 microkelvin or so. So this works pretty well. I don't want to go into the details anymore because I want to talk about collision experiments. Maybe Martin can show you a little bit more on the Sisyphus cooling scheme here. Okay, anyway, so this is the second step. The molecules come out of the bottle and they're cooled with collisions. And basically the idea is to cool the internal degrees of freedom from 300 Kelvin, the bottle temperature, to something like maybe a few degrees Kelvin. And this is a pretty standard device these days. So there's an inlet for the buffer gas, which could be helium or neon or something else. And then there's an inlet of a warm capillary, which brings in the molecules. The molecules then collide with the helium. They escape from the cell through a little hole here to make sure that they do not freeze in the hole. The hole should be open for a couple of hours or so to do experiments for a couple of hours. And then they're basically injected into a guide, and the guide then brings us to some further experimental stages like the deceleration stage. We tested a little bit this device here, the cooling scheme, how well this cooling scheme works, by interrupting the guide so that a few centimeters or so left open here, so the molecules leave the guide and they enter the next guide. That works surprisingly well. And in this region between the two guides, we can apply a homogeneous electric field, and this homogeneous electric field, and drive radio frequency transition between internal states. And we drive them from low field seeking states into high field seeking states, which in the end means that they're lost at the in the detection region. And from how many molecules are lost, we can say how many molecules were in that particular state. Okay, and if we then look at many states, we can determine the temperature distribution, internal temperature distribution, and this internal temperature distribution, for example, is shown here. This is keeping the cell at 18 Kelvin in this case. Neon is a buffer gas, and then rotational temperature that was observed depending on the pressure of the neon in the cell, here in units of 10 to 16 per cubic centimeter. The internal temperature goes down like 5 or until something like maybe 2 or 2.5 kelvins, something like this. So there's certainly plenty of cooling even below the temperature of the buffer gas due to supersonic expansion somehow. No? I will come back to that. So the price we have to pay for this, okay, there's nothing like a free lunch. The price we have to pay for this is a kind of velocity distribution which for these neon densities around 10 to 16 per cubic centimeter looks like a very sharply peaked, well, not maybe very sharply, but looks like a peak distribution, let's say around 200 meters per second in this case. 200 meters per second is not that cold. So that was kind of annoying for me when we made these experiments some years ago. Kind of annoying to see the molecules at these high temperatures, because at without buffer gas, just an effusive beam, no neon buffer gas or so, the distribution looks more like this, and there are plenty of slow molecules here at 50 meters per second and even below. But with the buffer gas applied at these densities, this is really zero. And the bad news about this zero distribution here, flat distribution at zero, is basically that these molecules are too fast for trapping. Okay, they're just too fast. They're 200 meters per second is a kinetic energy which is bigger than the trapping potential, which is typically around 1 Kelvin or so for electric fields that we can apply, let's say, around 100 kilovolt per centimeter. Of course, depending on the internal state. Okay, so what to do with these molecules? So the idea was to build a centrifuge, actually a reversely operated centrifuge. I will not go very much into the details, just show 1 or 2 plots for this. So it's basically a spiral-shaped guide, okay? It's not exactly looking like this, but it's a spiral-shaped guide, and it's spinning. It's spinning in this particular direction, and this is where the molecule is coming in with some high velocity. And we bring the molecule on this rotating disk, like this, and trap them in a continuous way, inject them in a continuous way, and then guide the molecules around this spiral or along this spiral guide while this whole thing is rotating. And while the molecules are going into the center, they of course have to climb the centrifugal barrier, or a centrifugal barrier in this rotating frame. And depending on the speed of the centrifuge, depending on the speed of the molecule, whatever, they come to rest right here in the middle. So what do we do with the molecules right at rest in the middle? Well, if you don't do anything, the molecule will just be reflected, basically, and then go back. So what we do is we take them away from this rotating disk and move them perpendicular to the disk, move them away on axis. And while they're going away on axis, there's no centrifugal energy or so that they gain when going away, because they stay on axis. So they come, they leave this rotating thing, they leave it with a speed of, let's say, a few meters per second. Let's say 10 meters per second. That's adjustable. So that works very nicely. It works in a continuous way. Here's a little bit a picture which is maybe a little bit more to scale. The molecules are coming in here. The molecules are guided in a ring, in a storage ring, basically, and they're picked up by this spiral-shaped electric guide, where you can see, so to say, from the top. And an experimental result for thermal velocity distribution, in this case from room temperature, basically, you can see that the flux of molecules at velocities, let's say below 50 meters per second, which are trappable, that this flux increases dramatically. Okay, it really goes up by, if you look in detail, several orders of magnitude here at low velocities. So that works very, very well. So now we combine it with a buffer gas cell. So here's a buffer gas cell. This is all the guiding here, this quadrupole guiding. There are different stages for, let's say, doing different experiments. This is a plate capacitor, which I've already talked about, for measuring the internal state distribution. There can be a detection region here. Let's say how many molecules are surviving this depletion spectroscopy region here. So we can bring in a detector here, for example. But otherwise, the molecules are just progressing or proceeding here through this guide. And then they go into this spiral-shaped decelerator and leave the decelerator on axis and have through some time of flight region here, which is roughly 25 centimeter or so, let's say something like this, into a detector, which is a quadrupole mass spectrometer. So that's how the system looks like, and we can bring in more or less any molecule that we would like to bring in. So we brought in several different molecules. One of our favorite is this one, CH3F. Another favorite is formaldehyde, H2CO, NH3. Well, we haven't really used NH3. We have done ND3, so that's a mistake here. It should be ND3. We operated it with methanol, for example. We talked about, in one of the previous talks, we had heard about methanol. It works pretty well, so methanol. And the biggest one we have used here is this one. Does any one of you know what this is? There are chemists in the room. Isopropanol, yeah, exactly. This is isopropanol. So it even works with isopropanol. Okay, it's just a couple of test examples, and you can bring in your favorite molecule maybe, and we can try that one. Okay. The only requirement, of course, is for guiding that it has a significantly large Stark shift in an electric field. So it should be a polar molecule, and it should have reasonably large Stark shift at the voltages that we can apply. So there's certainly some limitation if we go up to more massive molecule, because then at some point all these rotational states bend over and the molecule becomes a high field seeker. So these are still kind of small molecules. But I think this one is already, from my point of view, who is interested in single atom, single photon experiments, usually, this looks like a really fancy thing. Okay, anyway. Good, so this is some results. This is how the flux that comes out of the, measured in the detector. This is the flux that come out, something like 10 times 10 to 9, so 10 to 10 molecules per second, for two different experiments. One is operating the buffer gas cell in a kind of effusive regime, low buffer gas density, and the other one in a kind of supersonic regime, high buffer gas density. And for me, it was kind of a shock or kind of a surprise to see that the effusive regime works much, much better. The low buffer gas density regime gives much more flux than the supersonic regime. Please note, this is multiplied by a factor of 20 here. So it still goes up. It goes up, but we have to speed up our centrifuge maybe too much, and we don't want to do that. So 60 hertz is already quite something per second. I mean, 60 rotations per second. Anyway, so we have fluxes of the order of 10 to 10 per second, and densities in the guides then of something like 10 to 9 per cubic centimeter. And the question is, can we do collision experiments with this? And this is just a little estimate, and I would like to guide you a little bit through the estimation of our collisions to show you basically how little we know about the system. But knowing or seeing that we know little, it's surprising how far we can go, in my view. So the first thing is we calculate the total elastic cross-section for dipole-dipole collisions, basically. We know the dipole moment of the molecule and so on. So we calculate the total elastic cross-section at our temperatures, around 1 Kelvin, 10 meter per second roughly, corresponding to this 1 Kelvin temperature, or slightly below 1 Kelvin. We calculate the cross-section for the CH3F molecule of something like 2 times 10 to minus 12 centimeters squared. This is the order of magnitude of the collision cross-section for pure classical, let's say, dipole-dipole collisions. There's no detailed structure of the molecule entering into the estimation here. Then the total elastic collision cross-section in the guide is, of course, the density in the guide. It's multiplied with this cross-section that we just calculated times the relative velocity of the molecular beam. But this is what we know because we do time of flight measurements and we know what this velocity distribution is. It's roughly has a width of 10 meters per second of that order at least, and that gives a collision rate of something like 10 per second. That's expected. So whether we see this experimentally, let's see, but this is something that we expect. And the total number of collisions then depends, of course, on how far the molecules fly in the guide. And as I said, this is a few 10 centimeter. And then the number of collisions basically should be of the order of 1, maybe less than 1, but something of the order of 1 collision. So it's not a huge number, but 1 is also not so small. It's 1. And we should be able to see 1 collision in the end. That's the idea. So the idea is that the molecules are progressing in this guide after the centrifuge. They're progressing in this guide, they're moving, and of course with a velocity distribution, so there are slow molecules and there may be fast molecules coming from behind, and they make collisions, and if they transfer some momentum into the transverse direction, and if the corresponding energy transfer is larger than the remaining trap depth for that particular molecule, then this can lead to loss. So a large angle scattering can transfer longitudinal energy from the molecule into transverse energy. Then they leave the trap, like in this cartoon picture here. So we calculated this, how many large angle scattering events we can expect. We took the detailed energy distribution, so to say, in our guide. We know how our guide looks like. It's basically a triangular shaped potential. It's a quadrupole guide. We know the energy distribution of the molecules in the guide. And knowing all this, we can kind of determine how many collisions there are, or what the corresponding cross-section for these collisions are, for losses that occur via elastic collisions, dipole-dipole collisions, but that transfer enough energy so that the molecule is kicked out of this dipole guide. Okay? And this cross-section we estimate to be something like 10 to minus 11 square centimeter. So comparing this number with the total cross-section that we've seen before, we conclude that something like 1 out of 17 collision should lead to loss. We expect 1 collision in total, so 1 over 17 of this could lead to loss. So it's not a big number, but still. The next thing is this is elastic collisions, and now we come to the question, are there inelastic collisions? Well, inelastic collision, we have no idea of how CH3F molecules, for example, how they inelastically collide. I have no idea about this. So there are theorists maybe in the room who can help me, but I have no idea what's happening. So we make a very, very simple estimate, and the simple estimate basically says once two molecules have overcome the centrifugal barrier, then something is happening. Chemistry is happening, and we assume that this is loss. This comes completely out of the blue sky, but we just assume this. And so basically they go above this barrier, and then some complex forms that we don't know exactly. It's basically this Langermann model, which is kind of quite old, and we calculate for this a cross section of roughly 10 to minus 11 square centimeter. It really comes from blue sky, but this is all what we know basically. And that means in the end that 1 out of 13 collisions could lead to chemical loss. I call this chemical loss because something is happening, some reaction is happening. Okay, so we have 1 out of 17 collisions which lead to kinematic loss, and 1 out of 13 collisions could lead to chemical loss. I say could because it's not necessarily the case, could. And then when we do the experiment, well, the molecules are propagating along the guide, and there's a certain transmission over some distance. This is the time of flight distance. Of course, the loss depends on the density. It depends on the loss rate. Well, this is actually the time the molecule spent in the guide. This is the loss rate coefficient. It's cross-section times the velocity, as usual. And the loss cross-section should scale like the dipole moment squared, basically. So now we do experiments, and this is what we see. This is the velocity distribution as a function of velocity. So Vz is the longitudinal velocity between 0 and, let's say, 100 meters per second. and we do experiments for 4 different densities actually. One is a very, very small density, and this serves as a normalization, and this is basically the dashed line. And then for increasing density, and if you want, I can give you the numbers. They're not plotted here anyway. So for increasing density, we see this red, blue, and green curve, which basically shows that for low velocities, 10, 20, 30 meters per second or so, there's an increasing loss, increasing with density. It's basically what we expect. And from fitting the previous theory curve, we can basically compare our prediction for a dipole moment, in this case for CH3F of roughly half a dBi. We can compare the prediction of what we expect with what we observe, and what is predicted is something like 10 to minus 9, and what is observed is maybe 20 or 30% larger. So it agrees reasonably well, given that the model is so crude, really crude. But it agrees reasonably well at temperatures of our beam of, let's say, 0.8 Kelvin. So we can test a little bit on how that behaves as a function of the dipole moment. For example, we can change the molecule to ND3. ND3 in our case has a somewhat larger dipole moment. We know the internal state distribution, so this is averaged over the internal state distribution. But basically it's a little bit larger, and the effect that we see for low velocities, 10, 20, 30, 40 meters per second, is actually larger. It's 20% or so of the molecules which are lost. Again, for increasing density, we see an increase in the loss. And for this one, we can again also compare the prediction with the observation. In this case, it's slightly warmer, 1.1 Kelvin or so. The cross sections, or the loss rate is a little bit larger. 1.3 is the prediction, 2.1 is the observation. So there's a little bit larger discrepancy here, which we cannot totally explain because the model is very crude, because we don't know the density exactly enough. There are some error bars. We don't know the length, the time of flight, basically. We don't know exactly, because the molecules are already decelerating in the centrifuge, coming out of the centrifuge. So there's still some systematic thing that needs to be taken into account. And of course, we don't know the reactivity. We don't know the Langevin thing, basically. It was a very crude estimate. But we can take the ratio of these two loss rate coefficients that we measured for ND3 and CH3F, compare the observed with the expected one, and both are 1.9. Fantastic. So it scales like the dipole moment squared. And this finally convinced us, really, that we are seeing these electric dipole collisions. So we're claiming that this is the first observation of dipolar collisions between cold polyatomic molecules. How to proceed? Well, this is traveling molecules traveling in this quadrupole guide. Of course, the next step would be to put them into a trap. So now the system is extended. This is a centrifuge. You can see a side view here. The molecules are coming out of the centrifuge on axis, which is actually horizontal. So it's not going up, because the centrifuge is like this, put up. Okay. Anyway, they're coming out. The gravity doesn't play a role anyway. So at least not at these velocities. Well, who knows? Okay, the centrifuge is this vertical disk array here. The molecules coming out this way. We have a velocity filter here. It's propagating in a vacuum. No? And from here to there, it's about, 1 meter, maybe slightly more. So the molecules are propagating out, going through a velocity filter. We are taking away the fast, by bending this guide, we're taking away the fast molecules that are still coming out of the centrifuge decelerator, and are propagating in the guide as well, because we don't want to have them in the trap region. So there's this S-shaped region which has these sharp bends which serve as a velocity filter, and then basically we load the trap. Here's the trap, and then we let the molecules go out of the trap. There's a time of flight region to a quadrupole mass spectrometer which is located here. And we can load about up to, 4 times 10 to 8 molecules into the trap. So how does the trapping signal? This is a picture of the trap here. You can see the input guide. It's like this one. There's an output guide on the other side. And this is a trap. It's a very fancy trap. I don't want to go into the details. It's a microstructured electrodes which allow a couple of features that I haven't talked about. But for the present purpose here, it's not necessary to talk about this in detail. But this is basically how the experiment looks like. So this is a trap, and we load the trap. You can see some signal, for example. This is a signal as a function of time. We load the trap by sending in molecules. And the input is open to the trap. The output is, for example, also open. And then molecules are also flying through. And it takes some time for the molecules to fly through. This is a log scale. Please note this. It's a log scale, and then it's kind of filling. On a log scale, it continues to fill. Trap is loaded. We close the trap. We change the electrode voltages. We close the trap. We keep it closed for, let's say, 4 seconds here in this particular example. We open the exit hole. Molecules go out, and some exponential escape from the trap. So this is a typical signal, how it looks like. Okay? And this is a plot of the storage time. So normalized to 1 here. This determines a little bit, so to say, of how long we can keep the molecules in the trap. So this was 4 seconds here. 4 seconds would be this. So it would be this data point here. And we integrate over how many molecules come out. And then we see a plot like this with an average trapping time of a few seconds. So this is typical in this experiment, that we can trap a few seconds the molecules. Now the question is, how can we see collisions? It turns out, no, I don't have time to talk about this. I'm just telling you what kind of protocol we do to so to say check for collisions. So we do 2 protocols. One protocol is shown here, and it's called A. And the A protocol loads the trap for 2 seconds. Okay, so there's some loading, and we unload and see how many molecules come out. And then we just add the number that we get from here to the number that we get from there, and this number is just filling the trap for 1 second instead of the 2 seconds, and then seeing how many molecules come out. We add this number to this number and call this protocol A. So that's some number. Of course, the molecules in presence of collision would evolve like this, roughly according to this equation. In scenario 1, in scenario 2, it would evolve according to this expression, and of course there's exponential decay from the trap and so on because of the finite lifetime. So this is protocol A, and now we compare it with protocol B. So protocol B does nothing here, but does 2 loading sequences, basically one after the other, in the first 3 seconds. So we load for 1 second, and we load for another 2 seconds. This is a Mickey Mouse picture a little bit, no? of what you see here. So we load for 3 seconds, and here we load for 1 second and independently for 2 seconds. And here we load for 3 seconds in total and do nothing here. We call this B. This gives another number. And now because we have higher densities here, there should be additional losses. Additional losses in this scenario compared to the sum of these 2 scenarios. Okay, so the equations are basically following this one, and there should be an additional loss term, which is of this size. It's a number, or the density of molecules that we put in interval 1 into the trap, multiplied with n times this rate coefficient, which we want to know, if we see this, multiplied by 2, because basically it's a sum of the squared, and that gives a factor of 2 here. So there are additional losses. We are expecting additional losses, delta n, additional losses, which are of this order of magnitude here. Of course, the density in region or interval 1 is equal to the density in interval 1 in scenario in scenario A. So we can replace this by A. And if the losses are not too high, we can also replace the B by B. So we are expecting something like this. So we independently measure the N1 in A, scenario A, protocol A, and the N2 in protocol A, and we are expecting, as a function of hold time, an additional loss which is of this order of magnitude. And the result is plotted here. So this is this additional loss mechanism that we are expecting, and this is plotted on this axis. And on this axis is the relative loss, delta n over n. It's the relative loss that this additional loss, what we are expecting. And what we see is the blue data points. So it goes up, dip, dip, dip. So we make 4 measurements here, or 5 measurements, 1, 2, 3, 4, 5, for different densities. And this scales, if I plot it like this, it scales linear with the density as expected. And just from the slope here, we can just determine the rate coefficient, the collision and loss rate coefficient for this kind of measurement. So this is an independent estimation. It's the same kind of molecule that we used before in the free time of flight. But here it's for trapped molecules. It's a completely different experiment. And we arrive at this number, 2 times 10 to the minus 9 in these units. So if you remember what we measured before in the free time of flight, it was 1 times 10 to the minus 9. So there's a factor of 2 discrepancy. Ooh. We don't know the density so well, so there are probably some systematic. I don't want to claim that this is something which is really something important, but we are of the same order of magnitude. Please note this is work in progress. So yeah, okay. So the conclusion basically is there's first cold dipolar collisions for these polyatomic molecules. They are lossy, also they are elastic. We have a favorably good understanding, let's say, of what's happening. We have tested many molecular species, but we would like to improve. We would like to make it better. We need more molecules. Everyone needs more molecules. We need more molecules. So I've prepared maybe one more slide if you want to see them. Otherwise, I skip them if the chairman allows. So the idea is, where do we get more molecules from? Well, from the source. Well, the source is a bottle. Well, we can crank up the bottle, but that's not such a good idea. So it's basically the cryogenic buffer gas cell, which maybe needs some improvement. So the question is, can we get more molecules from a better effusive cryo source? There's a question to you I wanted to pose. So what do you think? If this is density of buffer gas, how would you think the molecular flux behaves as a function of density? Is it constant? And this is low density regime. It's not supersonic. This is low density regime. Is it something like constant? Or is it going down? And if yes, by how much? Or is it going up because we are cooling? And if yes, by how much? So what would you think? Posing the question to the audience.
Zero flux at zero density.
No, definitely not. If I take no buffer gas, then the molecules can just go from this inlet capillary just straight through to the output.
They are fast, they're not heavy. Okay.
Oh no, they just go through. If the measurement comes in a second. No, they are fast. So for zero helium, zero buffer gas density, which on this scale here maybe would be here, we actually see a huge flux. Okay, chairman is standing up. So this is the result. So this is in some normalized units because it depends on how many molecules we bring in. But this is really constant here. For low velocity is really constant. But then suddenly at densities of something like 10 to 14, we observe an enormous drop, 2 or 3 orders of magnitude. So it indicates a little bit that we haven't understood our cryo source reasonably well enough. So maybe in the audience there are people who did similar experiments before, but we were not aware. For me it was kind of surprising to see this. And we know what's happening, and this is summarized on this slide. Basically, we made a simulation. It's not a measurement. We made a simulation of how many molecules come out as a function of velocity. This is velocity here, and this is the escape angle, which is basically the width of the distribution of molecules that comes out of the buffer gas cell as a function of the number of collisions in the buffer gas cell, or as a function of the buffer gas density, if you want. And you see a dramatic behavior here. I don't want to go now into the details because time is out. But you see a dramatic decrease in the velocity distribution, in the flux. If you look at these numbers here, it's really going down. And there's also a huge widening. I mean, this is basically zero. To answer your question, this is basically zero density. There's 4,000 molecules. It's the highest flux we could ever achieve without helium. So it's the highest number. And then it broadens very much, 80 degrees or so. So it broadens very much. Anyway, so that concludes basically, but I would like to thank the group. I have a fantastic team, including Martin Ibrügger here, who shows a poster, I think, tonight. Isabel shows a poster tonight, and already advertised another talk by Martin Sittenfeld tomorrow. Thank you very much for your attention.
Maybe one quick, remark, question.
The question is that on the last slide, what was the Newton number for that data?
I don't know. The Newton number. Sorry.
The mean free path over the size of the orifice?
I mean, of course, first of all, this is a very simple simulation, Monte Carlo simulation, from which we take the average number of collisions. This is the density of the buffer gas and the number of collisions here. So everything you want to know should be included in this.
Out of the cell, or no?
No, this is, for example, here. Can you read this? It's 1.2 times 10 to 16 per cubic centimeter. This is a helium density. Well, it's not helium. It's just a hard sphere.
A much simpler question. What is this data meant to represent? Is this this is the simulation of what's coming out of the cell?
Yeah. Okay, sorry. Yeah, that's coming out of the
cell.
Yeah.
And that cell has a certain diameter orifice.
The specific geometry of our cell goes in. Yeah.
Right. So,
yeah.
So the question is, what is the mean free path divided by the diameter of that orifice for, say, the bottom one? The bottom
1.1 to 0.01.
Sorry?
1.1 to 0.01 in this range.
0.1 to 0.01, yes. So the mean free path is smaller than the orifice on the bottom one.
Yes, exactly, on the bottom one, but not on the top one. So we are in this intermediate. Basically, this is in the intermediate regime where we start having a free time of flight, which is longer than the cell dimension. Even the dimension, it's the top picture, and at the bottom it's shorter.
So your Monte Carlo takes into account hydrodynamics?
No, no hydrodynamic.
1 to 0.1. Maybe we talk afterwards.
No hydrodynamics here. Okay. This is still in a regime where hydrodynamics should not play a role. Because we don't know how to Monte Carlo simulate hydrodynamics.
But that's my point. So if you're at a ratio of 1, then hydrodynamics is playing a role. Because the mean free path is presumably the cell is larger than the orifice size. And if the mean free path is in the same size as
Maybe
the orifice.
Discuss it later.
No, there are more interesting things happening.
It's a major point of what I was saying at the end of this talk.
No, there's more interesting things. You see this decrease here, and what happens here? So it actually goes up. But this goes into a regime where our simulation we believe that our simulation no longer holds. But it seems to go up because then there is some hydrodynamic wind or something which brings out the molecules. But this is all in this windless region. Got it, good.
Thank you.
Okay, I'm sorry, we have to
Okay,
move on,
good.
I think. So let's thank Gerhard again. Next speaker is Mike Towers from the Material College, and he tells us about this fancy, nice stuff from this calcium fluoride experiment, maybe YBF2. We will see. Thank you very much. You can join Mike. Go ahead.
Okay, thank you very much. It's really a huge pleasure for me to be here. Many of the applications of cold molecules that we're also keen on require long coherence times. And we heard already this morning from Yuval about long spin precession times, which are so important for EDM measurements. And probably many of you know the wonderful work done at MIT demonstrating second scale coherence times on the hyperfine transitions in molecules, which of course is important because the hyperfine states can be used as storage qubits. And rotational coherences, of course, are also very important for our field. So, as an example, if you want to couple the molecules together, you'd like to probably do that using the dipole-dipole interaction and to do that in a controlled way. And a good way to do that is to use the oscillating electric dipole moments that you have when the molecules are in superpositions of rotational states. That's what Eric already showed us this morning already. So, in order to have high fidelity interactions of that kind, we would like to have long rotational coherence times. How long is long enough? Well, let's think about a couple of examples. So if I imagine taking a pair of molecules and they're in tweezer traps, and I bring them as close as I can together in the tweezer traps, which is probably about half a micron, then in that case the strength of the dipole-dipole interaction is a few kilohertz. Okay. Another example would be trapping molecules magnetically close to the surface of a chip in microscopic magnetic traps and coupling the molecules to one another via a superconducting microwave resonator. And in that case, you can expect to have coupling strengths between the molecules of some tens of kilohertz. Okay, so in both examples, in order to have high fidelity quantum operations, you would like to have rotational coherence times that are, let's say, tens of milliseconds or preferably even longer. There's been quite a lot of work recently looking at rotational coherence times in optical traps and recent demonstrations showing that you can get rotational coherence times of about 10 milliseconds in optical traps. I think we'll hear about that work tomorrow. But there hasn't really been very much work on coherence times in magnetic traps, so that's what I want to tell you about today. So let me begin just by telling you about some of the methods that we use to make our cold molecules and put them into magnetic traps. So we use mainly calcium fluoride molecules, and our experiments begin with a magneto-optical trap of calcium fluoride. So the experiment is illustrated here. It starts over here on the left-hand side with a cryogenic buffer gas source of these calcium fluoride molecules. So this source emits short pulses of molecules traveling at about 160 meters per second. We slow these molecules down using the radiation pressure of this counter-propagating laser light here. And this laser light is frequency chirped in order to compensate for the changing Doppler shift as the molecules slow down. So then the molecules are decelerated. We decelerate them to about 10 meters per second. They arrive in the center of this vacuum chamber here, and then we capture them in a magneto-optical trap. This slowing step of the experiment, it requires just two lasers. So the main slowing light drives this 0 to 0 band of the B2X transition. It's at 531 nanometer. And then we use a single repump laser to repump the population that decays to the first vibrationally excited state of X here. So just two lasers. And then for the MOT, we use 4 lasers. The main cooling light drives this A to X transition. It's at 606.3 nanometers. And then we use another 3 lasers as repumps to repump the population that decays to the higher lying vibrational states of X. Okay. So I won't go into the details of all of the energy level structure today, but let me just point out one important thing, which actually Jun-Yi already pointed out yesterday. So in all cases, we drive a transition from the ground electronic state with 1 unit of rotational angular momentum up to the excited electronic state with no rotational angular momentum. Okay, so this n here is the rotational quantum number, and we drive the transition from n equals 1 to n equals 0 in all cases. So this works very well. Here's a picture of one of the first MOTs we ever made. It's a picture taken on the CCD camera here of the laser-induced fluorescence from the MOT. And this MOT contains about 2 times 10 to the 4 molecules. The density is 2 times 10 to the 5 per cubic centimeter. Temperature, it's about 12 millikelvin. The trap frequency in the MOT, it's about 100 hertz, and the lifetime of the MOT is about 100 milliseconds. So this temperature here, this temperature is rather high, and so in order to get the molecules colder, the next thing we do is to apply sub-Doppler cooling. And again, Jun-Yi already pointed out yesterday that when you have this structure here, where you have more angular momentum in the ground state than you do in the excited state, then the sub-Doppler mechanism, the Sisyphus mechanism, requires blue detuned light. Okay, so for the MOT, of course, we're using red detuned light. The Sisyphus cooling requires blue detuned light. So that's the next thing we do. We go through the following steps. We first of all load the MOT at full laser intensity. That captures the largest number of molecules. And then we ramp the intensity down to about 1% of its initial value. That brings the temperature down to a little bit below a millikelvin. And then we just switch off the magnetic field of the MOT, switch the light to a positive detuning, typically about 20 megahertz, and then turn the intensity back up again, so that now the molecules are sitting in this blue detuned optical molasses. It's the gray molasses that Jun talked about yesterday. So this is very effective at cooling the molecules to sub-Doppler temperatures. This is our measurement of the temperature coming down as a function of the amount of time they spent in the molasses. And very quickly, after half a millisecond or so, they pass below. This dashed line here is the Doppler limit, 200 microkelvin for calcium fluoride. We measure the temperature by the standard ballistic expansion method. Here's some pictures of a cold, ballistically expanding cloud. And then we see a temperature typically of about 55 microkelvin. Now this temperature here, this is limited by the random nature of the spontaneous emission, okay, which is a heating mechanism, of course. So ideally we would like to turn that off. And a good way to turn that off is to arrange for the slowest molecules to get optically pumped into dark states, so they're no longer scattering photons once they're slow enough. So that's the next thing we do. We actually apply a second stage here of sub-Doppler cooling. So let me explain how that works. What I'm showing you here, this is the laser cooling transition, going from the ground electronic state with n equals 1 up to the excited state with n equals 0. And there's some hyperfine structure. Okay, so this n equals 1 state here has 4 hyperfine components due to its coupling with the electron spinner half and the nucleus spinner half. And we add radio frequency sidebands to the laser light so that we can drive all 4 hyperfine components. Okay, it's essential to do that in order to make sure that the scattering rate is high enough that the MOT works, and also actually that this first step of sub-Doppler cooling works. But now once we have the molecules down, cooled to about 50 microkelvin, we actually just turn off the radio frequency sidebands so that we're left with just a single frequency of light here. Okay, and the single frequency is blue detuned from all of the transitions. Now once we just have this single frequency of light, there are dark states in this system. Okay, and in particular, there are dark states amongst the F equals 2 levels here. For our particular polarization configuration, which is counter-propagating sigma plus, sigma minus beams, there are 2 dark states. So there's this one, which is the superposition of the m equals minus 1 and the m equals 1 state. And then this second dark state, which is the superposition of m equals minus 2, m equals 0, and m equals plus 2. So the molecules get optically pumped into these dark states. And now if the molecules are moving quickly enough, then they can non-adiabatically transfer out of the dark states. Okay, so these are robust dark states for molecules at low velocity. Right, so it's a velocity selective coherent population trapping. So these 2 ingredients, okay, we still have this blue detuned light, which is giving a Sisyphus cooling, and we have these velocity selective dark states. Those are the ingredients you need to be able to cool to much lower temperatures. And here you see our measurement of the temperature coming down as a function of time that we apply this second sub-Doppler cooling step. Once everything is optimized, we get a temperature of about 5 microkelvin. So now we have these cold molecules. The next step is to put them into a single quantum state and then trap them magnetically. So here again, this is the n equals 1 rotational state of the molecule with its 4 hyperfine components that I showed you on the last slide. And I've drawn in here the Zeeman sublevels of each state. And 20.5 gigahertz below is the rotational ground state, n equals 0. It has these 2 hyperfine components. So first of all, we optically pump the majority of the molecules into just a single state. We choose this state here, the F equals 0 state. And then we actually drive this microwave transition here to drive the population down to this state, F equals 1, MF equals 1. So the population is now shelved in the rotational ground state. We then apply a pulse of light which just pushes away any population that remained in n equals 1, so that now we can be sure that we've got all the molecules in a single quantum state. And then actually we typically transfer the population back up again to n equals 1, and we can choose which state we want to go to, but we would very often choose this state here, F equals 2, MF equals 2. Okay, so now we have molecules in a single quantum state that we can choose, and these states that I've selected here, this one and this one, you see they're weak field seeking states, so these are magnetically trappable states. So the next thing we do is to turn on a magnetic quadrupole trap, and that confines the molecules. This is a measurement of the loss rate out of the magnetic trap as a function of the amount of helium that we flow through the cryogenic source. Okay, so this cryogenic buffer gas source has helium flowing through it constantly. That helium is incident on the magnetic trap, and the loss out of the magnetic trap is dominated by collisions with the helium. Okay, so you can see the loss rate depends linearly on the helium flow rate here. And actually we did this measurement with molecules in 2 different quantum states, this one here and this one here, basically as a sort of proof of principle demonstration that we could do collision experiments with molecules in single selectable quantum states. So once we understood that the loss rate here was limited by this flow of helium, we actually installed a helium shutter that shuts off the flow of helium once the molecules have passed through. And then after installing this helium shutter, we get a trap lifetime. We get a loss rate down here, which corresponds to a trap lifetime of 4.5 seconds. Now the molecules can be excited. They can be vibrationally excited by black body radiation. And if you calculate what is the rate for that process for black body radiation at room temperature, it's this value here, 0.22 per second, which is exactly the loss rate that we're measuring. Okay, so the loss of molecules from the magnetic trap here is dominated entirely by this black body heating process. Good, so now we have molecules in the magnetic trap. We can choose which state to put them in. So now we start to prepare superpositions of the rotational states and look to see how long the coherence survives. If you want to do these 2 things, so we want to have magnetically trapped molecules and we'd like to have long rotational coherence times. Okay, that requires that we find states that have large Zeeman shifts so that we can magnetically trap the molecules. So large Zeeman shifts, but also identical Zeeman shifts for a pair of states. Okay, so that there's no dephasing in the system. Yeah. So I show you here again the n equals 1 rotational state, the lowest rotational state. This is the same as I showed on the last slide. I'll also put in, this is the second rotationally excited state, n equals 2, sitting 41 gigahertz. Above, it also has these 4 hyperfine components, and I've drawn in here some magnetic sublevels. And now let me just draw your attention to the states that I've highlighted in purple here. Okay, these are the stretch states of the system, the states that have the maximum possible value of the projection quantum number for each rotational manifold. And these stretch states, they have nothing else to couple to. Okay, so they have perfectly linear Zeeman shifts at all magnetic fields, and their Zeeman shifts are basically the same as that of a free electron. Okay, so the stretch states have magnetic moments very nearly equal to the Bohr magneton. The Zeeman shifts are 1.4 megahertz per Gauss. And that's true for all of the stretch states. Okay, so we should have magnetically insensitive transitions between these stretch states. For example, the 2 that I've drawn in here, they should be magnetically insensitive. And then that raises an interesting question. Okay, so how magnetically insensitive are these transitions exactly? Okay. In order to answer that question, we need to take a look at the Zeeman Hamiltonian. So here it is. Let me just take you through this. So this first term here, S dot B, that's the normal electron-spin interaction. You're all familiar with it. And that's giving the 1.4 megahertz per Gauss. It's by far the dominant term in the Hamiltonian. And it's just the same for all of the stretch states. Okay. And then we have this term here going like I dot B. It's the nuclear spin interaction. Of course, it's much smaller. And it's also the same for all of the stretch states. Then there's this guy here going like N dot B with the coefficient GR. This is coming from the very tiny magnetic moment that's associated with the rotation of the molecule. Yeah. And because it's associated with the rotation of the molecule, it depends on the rotational state. It depends on N. And then there's this other term here, which is usually called the anisotropic part of the electron spin interaction. Okay, it has the coefficient GL. It goes like S dot B minus SZ BZ. Z here is the internuclear axis. Okay, so this is expressing the idea that the response of the molecule to a magnetic field is a little bit different when the magnetic field is along the internuclear axis relative to perpendicular to the nuclear axis. This term also depends on the rotational state, depends on N. So from the Zeeman Hamiltonian, you can then very easily work out what is the Zeeman shifts of these stretch states, and I write down here the difference between them. Okay, so this is the Zeeman shift of the stretch state in manifold n plus 1 minus the Zeeman shift in the stretch state with in manifold n. Ideally, this would be 0. Okay, it's not 0. It gets a contribution from this term here going like GR and a contribution from this last term here going like GL. And this first term has no n dependence, and this second term has some n dependence. Okay, so we went about in the lab measuring the residual magnetic sensitivity of these transitions here. They're supposed to be almost magnetically insensitive, so to measure their residual sensitivity, you need to be able to measure small frequency shifts. We do that by Ramsey interferometry. Okay, so here's some data showing some Ramsey fringes as we scan the frequency of this 20.5 gigahertz microwave here. And from data such as this, you can very accurately find the center frequency and then do that for various applied magnetic fields and find out the magnetic sensitivity. So here's the results for these two transitions here. So what we find is that on this lowest transition at 20.5 gigahertz, we get a dF by dB of minus 105 hertz per Gauss. You can express that in a different way. It means that the difference in magnetic moments between the lower state and the upper state is this number, minus 7.5 times 10 to the minus 5 Bohr magneton. And then this one here, this is the 41 gigahertz transition shown in red here. This dF by dB is just minus 4.6 hertz per Gauss, which means that the magnetic moments of the two states, here and here, are equal to one another to within 3 parts per million. Okay, and now knowing these magnetic sensitivities, we can figure out what are the values of GL and GR, the parameters that appear in that Zeeman Hamiltonian. These are our experimental values. Our collaborators, Jesus Aldegunder and Jeremy Hudson, they've calculated these values for calcium fluoride, and they're also calculating for other molecules. And you see that the experiments and the theory are in good agreement. And then knowing these values of GL and GR, you can now deduce the magnetic sensitivity of all of the stretch transitions, okay, for every n. So here's the answer. It's expressed here as the difference in magnetic moments between the lower and upper states. This blue point here, that's the lowest transition, the 20.5 gigahertz transition, and its magnetic sensitivity, it's actually dominated by the GL term. And then as you go up to high values of n, you get a plateau here. The sensitivity is dominated by the GR term. And then here, this point here, which corresponds to the 41 gigahertz transition, these two contributions cancel each other almost exactly. Okay, so you have two small contributions that also cancel each other. And it's that's responsible for this tremendously insensitive transition here. Good. So then, of course, we wanted to see, well, what rotational coherence times can we really get in the magnetic trap? So we did the measurements for both of these transitions. So here's some data showing the coherence time on the 20.5 gigahertz transition. These are Ramsey fringes, okay, as we scan the free evolution time between the two pi/2 pulses of the Ramsey sequence. Okay, so the microwave oscillator is slightly detuned from the rotational transition, and we just see the beat note between the oscillations of the oscillations of the molecule and the oscillations of the microwave field. That's this beat note. And the decay of this beat note gives you the coherence time. So on this transition here, we get a coherence time of 0.6 milliseconds when the axial field gradient is 30 Gauss per centimeter. On the 41 gigahertz transition, which of course is the better one, less sensitive to magnetic fields, this is the data. You have to notice the change in the time scale here. We get a coherence time of 6.4 milliseconds. In this particular case, the field gradient was 45 Gauss per centimeter. So this coherence time here, is already getting to be pretty useful, and it's also interesting to think about what is limiting it. And we've been modeling the experiment and actually find nice agreement with the data. So in these experiments here, the limitation is actually the very large size of the molecular cloud that we have. Okay, so we take this very large distribution of molecules, it's a few millimeters across, and put it into the magnetic trap. And now the range of magnetic fields that the molecules see is governed by the initial size, this large initial size of the cloud. Okay, so actually, if we could compress the molecular cloud, make it a lot smaller, then we would expect these coherence times to go up in proportion. And it's interesting to think, what is kind of the fundamental limit of the coherence time you might expect here. So I like to think of, compressing the cloud to a very tiny point and then putting it into the middle of the magnetic trap and then let it go and it sloshes around in the trap. And now the range of magnetic fields that the molecules see is now just determined by the temperature. Okay, so the temperature tells you the range of magnetic fields that the molecules see. The range of magnetic fields tells you the range of transition frequencies, and that tells you what the dephasing time will be. So the answer to that, in what I call in the temperature-limited regime, you would expect the coherence time to be 7 seconds per microkelvin. Okay, if the molecules were if you could get into this temperature-limited regime and get the molecules at a microkelvin, the coherence time would be 7 seconds. Obviously, we're very, very far away from that, but I like to put this up to show you what might be achievable in the future. Now, of course, you also might wonder, are there other decoherence mechanisms that actually have nothing to do with the magnetic trap? So we also looked at the rotational coherence times in free space. It's again on this 41 gigahertz transition. So here's the data. In free space, we see a coherence time of 16 milliseconds. And this is just limited by the random motion of the molecules. Now they're not trapped. This experiment was done at 50 microkelvin. So the molecules just move in a straight line in a random direction between one pi/2 pulse and the next pi/2 pulse. That changes their phase in a random way, and that's what's responsible for the dephasing here. That dephasing you can actually take out with a spin echo. So we do that, we apply the spin echo, and now we see much longer coherence times. Here's the oscillation still going on after 32 milliseconds. And actually, in this case, once we apply the spin echo, we actually couldn't see any decoherence at all. We see the loss of molecules because the cloud is expanding and dropping out of the field of view, but we couldn't see any decoherence, and we set this lower limit to the coherence time of 47 milliseconds. Okay, so that's the story I wanted to tell you about coherence times. Do I have a couple? Then I just take a minute or two to say about some current directions with calcium fluoride in London. So we're trying hard to look for collisions between calcium fluoride molecules and rubidium atoms. Actually, already about a year ago, we made a dual MOT of calcium fluoride molecules and rubidium atoms. This is a picture of the two MOTs together. and we were able to load both species together into a magnetic trap, and we actually looked for collisions between the two species. We couldn't see anything, and really the reason is that we retrofitted a rubidium MOT to the calcium fluoride MOT. So we just added a rubidium dispenser and tried to load from the background rubidium vapor. And when you do that, well, you can get a lot of atoms, but you can only get a lot of atoms when you have a high background pressure, in which case you have a short magnetic trap lifetime. So we need both. We need lots of atoms and a long magnetic trap lifetime to be able to see collisions. So to that end, we've built now a new apparatus. Here's a little photograph of it, where we load the rubidium via a 2D rubidium MOT on the sidearm here. That loads 3D rubidium MOTs very, very rapidly, and we actually make really huge MOTs. And just in the last week, we were able to get our first calcium fluoride MOTs into this new machine. So we're optimistic that we'll be able to see collisions between the two species pretty soon. If you want to know more about this, then Hannah has a poster, so please ask Hannah about the details. And we're also trying to get molecules into tweezer traps, and to do that, we've built an apparatus to do that. We actually couldn't see any way to put the lenses needed to make the tweezer traps into our MOT chamber and still have a MOT. So we've actually built this in a second vacuum chamber, which is connected to the MOT chamber with magnetic transport from one place to another. And we're working hard now to try and get all of that up and running. So with that, let me finish, and let me thank all of the group members, both past and present, who've contributed to this work. Let me especially highlight Luke and Hannah and Stefan. They're all here at the front, and Stefan is now at the Fritz Haber Institute. These are the three people who've really been instrumental in making all of this stuff happen. And then let me thank you for your attention.
Plenty of time for questions now. Yeah, please.
Mike, in terms of coherence, then there is T1 and T2. I assume what you measured is T2.
Yes.
But in the introduction, when you said you want to have a collisional, rotational superposition state for dipole-dipole interaction, at that point I think it would be T1 which would matter, and not T2. So it's a driven at least.
I think it may depend on exactly the protocol that you plan to use. I mean, what I have in my mind is a kind of Ramsey sequence where you get an additional phase due to the dipole-dipole interactions, and so I feel like in that sense it ought to be the T2 that matters. But you've questioned it, so I should clearly think more. Yeah.
Please just make a comment. In our 3D KIV experiment, when we watched the dipole exchange, indeed you can see on the Ramsey fringe, you see exchange interaction energy is short as the fringe oscillating back and forth. And the longer the T2, the better for you to do Fourier transform and isolate all these different interaction energies by dipole exchange enabling cycles.
Yeah, thank you.
Yeah. When you see these long-lived coherences, are you limited at all by how many fringes you can fit in there, or you can sort of shrink and expand this within the coherence time?
You mean how many oscillations that we get? No, I mean the number of oscillations you get is determined in these experiments. Just determined entirely by the detuning that you choose between the microwave frequency and the transition frequency.
So you can control the flopping rate.
You can control the flopping rate, no problem at all there. Yeah. So we just, I mean, this is done. I forget. I think this is done with a 200 hertz detuning, and you can read it off.
So can you apply electric fields to play around with the GL and GR?
That's an interesting question, and we've thought a little bit about various ways that you might tune away this residual difference in magnetic moments. What I think is so I think yes, in principle you can do that. What's what I think is difficult is to do that in the environment of the magnetic trap, where the magnetic field is all over the place. And now, I think could find a scheme where, you apply a magnetic field, an electric field, let's say, that has to be parallel to the magnetic field, and then maybe you can tune it away. But you can't organize that everywhere in the trap. So we had trouble finding a scheme where we thought it would work in the environment of the trap. But I think that's worth thinking through, because
Perhaps if you use yield friction.
yes, that would certainly help. Yeah.
In your thought of the delta G, you have this lucky crossing through zero. Is that lucky, or do you know if you change the alpha and earth atom, is there always a crossing like that?
So Jeremy and Jesus are doing the calculations for other molecules, and I think we don't yet have the answer for you, but in a matter of weeks, I think we'll have the answer. Yeah.
So you said that your in-graph lifetime was about 6 milliseconds. Sorry, not coherence time was about 6 milliseconds, but in free space it can be a factor of 10 bigger. And so it's because of the inhomogeneity, like how much magnetic field radius. Could it also be related to the higher density when it's in the trap? Like if you make it into a very tiny volume, are you going to be limited by some other density-related effects?
So at the moment, we're certainly not at all limited by density effects. I wish we were. But I think that you're right, that if we could go to higher densities, and if we could get to much longer coherence times, then at some point you hit a density limit. And that's already been seen in investigations in optical traps, that the density plays a role. Yeah.
Any more questions? No? Coffee break. Before you all move to the coffee, if you have a poster, then there's Naomi and Alice outside will guide you to the poster boards that are close to the library. So please put them out. turn it on. Nothing yet.
John's was doing it. It worked when we plugged this in a moment ago. Let me try again.
Just do this one.
It always... There it goes. How do we get rid of that? Sorry, I've never used that screen. How do I get rid of that? Okay.
Okay.
Cool.
We go. So again, Jeremy Hudson from Durham University for non-reactive ultracold molecules decay via complex formation.
Well, again, thank you very much to the organisers for inviting me to this wonderful meeting. It's one of the most exciting places I've been in a very long time, and I'm having a great time here. We've heard quite a lot already about the question of how ultracold diatomic molecules collide with one another and whether they form complexes when they do, and my talk is another one on that topic, based on how the interpretation of some recent results from Simon Cornish's group on collisions of RBCS molecules. As I think everyone in this room knows, there are quite a number of groups around the world who can now make ultracold polar alkali dimers, typically 1 microkelvin or below, in optical traps, magnetoassociation followed by stirrup. It all started more than 10 years ago now, back in Gila with KRB. That was a fermion, and so KRB plus KRB collisions were protected. KRB was protected from another KRB molecule if it was in the same state. And so Junyi's group measured these very slow but temperature-dependent loss rates for KRB. But if they put half the molecules into a different hyperfine state, then S-wave collisions were allowed and the loss went a great deal faster. And everyone was thinking that that meant that bosonic molecules would decay very fast if they could, and it led to many groups trying to make bosonic molecules that couldn't decay by that kind of reaction. So that led to molecules like rubidium-cesium, sodium-potassium, sodium-rubidium, and many more come along or just about to come along. But we fairly quickly found that all experiments using bosonic ground state molecules seemed to show fast collisional decay, even though we thought there wasn't a two-body pathway. And this talk is really about trying to understand what's going on in rubidium-cesium plus rubidium-cesium with some fairly detailed measurements and theory on that system. Now, when we're doing theory on simple collisions of relatively simple particles, and that means atom-atom, sort of 2 cesium atoms, or a simple atom plus molecule system, helium NH or something like that, what we're used to doing is close coupled channel calculations, essentially full quantum scattering calculations, putting in the full complexity of the atoms and molecules that are colliding. And that's perfectly feasible for these small systems, mostly the atom-diatom systems, and not particularly heavy atom-diatom systems at that. And I would just like to plug our MolSCAT program. We've got a new 2019 version of MolSCAT that's now available and on GitHub for anyone who wants to pick it up and play with it, with 200 pages worth of manual. However, such calculations become pretty heroic, even if you want to do something like lithium plus calcium hydride or lithium plus calcium fluoride, getting a bit heavier and with deep wells, or K plus KRB. They're not only heroically expensive, but they're also pathologically potential dependent. But by that, what I mean is that if you have an interaction potential and you change it by 1 part in 10 to the -3, which is far more accurate than it can be, the results get randomized. And so although you can learn some things about the general properties, you can't just take a potential and do calculations and have any realistic expectation that the numbers you get will be meaningful. When you come onto systems like RBCS plus RBCS, you can't do the full calculation at all. We just don't have the theoretical methods available to do the exact collision calculation. So we have to turn to approximate methods of one kind or another. And there are two classes of approximate methods that I'd like to say a little bit about in this talk and try and relate to one another. One is ideas of universal and non-universal short-range loss, and the other is models of sticky collisions, collisions going via complexes. I'm going to start by saying a little bit about both those ways of thinking about these complex collisions. So first of all, this business of universal and non-universal loss, which Igiashek and Julian really came up with to explain the original KRB plus KRB results. The basic idea is an idea from quantum defect theory, which is that an attractive r⁻⁶ potential has quite a sudden onset. And so a lot of the scattering bounces off that even though it's attractive, a lot of the scattering bounces off the fast onset of the attractive potential and never makes it to short range. Quantum defect theory allows you to work out how much of the scattering actually gets past the attractive potential and reaches short range. And then for those that do reach short range, you think in terms of there being some probability for them just being sucked into products of some kind, and some probability that's 1 minus that for them to be reflected back out. And that tends to be expressed in terms of a parameter that was introduced and called y. It's not the probability itself, but it does have the property, the probability is actually this thing, but it does have the property that when y is 1, it means that everything is absorbed, and when y is 0, it means that everything is reflected, or at least everything that gets to short range is reflected. So you can think of y as a sort of a partial absorption and partial reflection for the collisions that get to short range. If you have 100% short range loss, that's called the universal limit, and it gives a particular loss rate that depends only on C6 and the coefficient of the dispersion attraction and the reduced mass. And when you plug through the numbers of that, you get a particular number that's about 10 to the minus 10 cc's per second for rubidium-cesium colliding with itself. Key thing about the universal limit is that there is no reflected wave. Everything gets sucked in. If there is no reflective wave, it doesn't matter a damn what the phase of the reflective wave is. And so there are no resonances, and the universal rate is the same for all systems where everything is sucked in at short range. An important point, though, is that the fact that you're in the universal loss limit does not mean that there's no elastic scattering at all, because a lot of the collisions at low energy do scatter off the attractive potential. Those ones never get to short range. Those ones are reflected back. So you have a very well-defined and quite large cross-section for elastic scattering, even in the universal limit. Now, that's universal loss, but then you can have non-universal loss, and non-universal loss is just generalizing that to take account of the fact that less than 100% is absorbed at short range, some fraction is reflected. That fraction does need to have, there's a phase now for how that gets reflected at short range. So there's both the non-universal case, there's both this fraction of reflection, fraction of absorption, and a short range phase shift. And that short range phase shift maps onto a scattering length. It's not the scattering length, but if you know the long range behavior, you can translate it into a scattering length and vice versa. The other thing is that the original form of these universal models and the non-universal model was for S-wave scattering, but when you go to higher temperatures, you do need non-S-wave scattering, partial waves that are non-zero. Actually, you can do that within exactly the same framework. Bogau has told us the analytic solutions for an R⁻⁶ potential with and without centrifugal corrections. So it's a little bit more complicated, but you can fit it into exactly the same conceptual framework, and all these things about particles getting trapped behind centrifugal barriers and bouncing off centrifugal barriers just happen. So it's not too difficult to build in. If you've got a non-universal model, then what it gives you is a total loss rate coefficient. It does not give you product state distributions. It just tells you a rate coefficient for all the loss processes. It's a function of the collision energy, at least the way that we've formulated here, which is really quite similar to the way that Svetlana formulates it. There are only two parameters in these universal models. There's y and delta, the fraction of loss and the short-range phase, and as I say, delta maps to a scattering length. So it's useful to look at some contour plots of what happens. This shows you a rate constant for universal loss. Y equals 1 up here means universal. And this is a rate constant as a function of energy at the moment. And down here is the short-range phase, but in the universal limit, the loss rate is independent of the short-range phase. Then we can start varying y from universal. If it's 50% loss, you've got some fairly slow dependence on the short-range phase. We can go on 20% loss, 10% loss, 1% loss. So you can see that we're just increasing the amount of structure. This is actually an S-wave resonance. This is S-wave resonance scattering. These other things that crop up at different values of the phase, in other words, different values of the scattering length, are at other kinds of resonance. This is actually a D-wave resonance. This is a G-wave resonance. This is actually for identical bosons, so you don't have the odd partial waves in this one. So we can get these contour plots, and, well, I'll come back to using those contour plots in a moment. However, if we're dealing with these alkali dimers, how can these ideas of universal and non-universal loss apply anyway? They're all very well, but there aren't any two-body loss channels, so why are we talking about two-body loss? Where do the molecules go? Now, this is where we come into John Bone's ideas of statistical counting of numbers of channels related to the kind of thing that Thijs Carmen was telling us about yesterday. Before I talk about that, though, I do want to throw in a caveat about it. We tend to think classically, or half classically, I won't say semi-classically, of scattering that either bounces straight off or scattering that gets caught in a resonance and sticks around for a while and then bounces off. And that's all very well, and that's quite a good picture at higher energies, and it's well formulated and well understood. It goes back to Eisenbud and Wigner, long time ago. And in quantum scattering, we can define this time delay, and you actually just get it from the energy dependence of the scattering phase shift. Felix Smith told us how to generalize that to a lifetime matrix for multi-channel scattering, but this is really for energies above the ultracold regime. And there, it's true that non-resonant collisions are usually short-lived, and the time delay peaks at resonance. So you get something like this green picture, which shows how the time delay, this shows the time delay peaking at a resonance with a much lower background than at resonance. Unfortunately, this doesn't really work once you get into the ultracold regime. In the ultracold regime, it turns out that the at low enough energy, the time delay is just proportional to the scattering length, and that can be both positive and negative. And so most of your ideas of resonant scattering being long-lived don't work properly. That's not something I want to go into in this talk, but I just want to flag up that the whole issue is more complicated than most people seem to think it is. However, let's go back to the sticky collisions idea for cold molecules. It goes back to these papers by Myler et al. In John Bone's group. And they came up with a statistical model, and they pointed out that both 3-atom and 4-atom collision complexes have pretty deep wells, and that if you evaluate the density of states at the top of those wells, you get very large numbers. This is exactly what Thijs was talking about yesterday. Thijs sort of corrected the original numbers that John Bone came up with, but still the principle is that you get pretty large numbers. And if a long-lived complex is formed, it's possible that it gets destroyed before it falls apart again to give you your original molecules back. John Bone's original idea was that it would be destroyed by collision with a third body. Thijs talked about that being a laser-driven process, and those are true. We need to understand what's happening. But either way, you get, if the formation of the complex is the rate-limiting step, you get second-order kinetics for the decay of the molecules, not third order. So even if it is a three-body process involving two coming together and a third one coming along, provided the lifetime is long before a third body comes along, you still get two-body kinetics. And in Thijs's model of it being a laser, you certainly get two-body kinetics. So the original estimates gave, a 10 to the 2 to 10 to the 4 levels per Kelvin for triatomic ones, and more like 10 to the 9 levels per Kelvin for tetraatomic ones. Those, everyone recognized that those were very drastic dynamical approximations, and as Thijs pointed out yesterday, those are estimates, possibly overestimates by several orders of magnitude. But they made another key approximation, which is that they assume that all the levels that are there are statistically sampled. And they introduce that in a particular way. They have a mean level width, gamma, which is basically equal to the level spacing with this additional factor of the number of open channels in front. And that's an approximation that you can see that comes from various possible places. You can think of it as coming from our RKM theory. You can think of it as coming from random matrix theory. They estimated a lifetime of 45 milliseconds, as Thijs said yesterday, probably really much shorter than that. But they had another key result, and this key result's in their second paper. And the key result is that provided the complexes last a long time compared to whatever destroys them, it doesn't matter what the density of states is. Under those circumstances, you get the same loss rate as the universal limit, which comes from a completely different derivation. At least in the ultracold limit, you get the same result. So even if complex formation is what's going on, it's really useful to use these universal and non-universal ways of thinking about it, and then maybe interpret the results of that in terms of these ideas of mean widths and mean lifetimes of the complex. So that's sort of the theory background. What Simon's group have done are that they've taken clouds of RBCS and measured the lifetimes, measured the time-dependent loss profiles for them. And they've done this for the ground state and for some hyperfine excited states and for some rotational excited states, but I'm only going to be talking about the ones for the absolute ground state today. And this is the first point, which is here's the time profile of the loss, and here are fits to it to this formula, so, which is for first order, second order, or third order kinetics. I don't want to say two-body, three-body, because order and body are not the same thing. But this loss profile very nicely fits the second order kinetics, and it really doesn't at all fit either first order or third order kinetics. And they verified that by varying the initial molecule number, and okay, there are big error bars on here, but again, first order and third order are both a long way away from what they observed. So this is pretty convincingly kinetically second order loss. So that really, so far, that does support a mechanism that goes via complex formation. It's quite hard to come up with anything that gives you a rate determining step that's second order, except complex formation. However, when you look at the actual numbers, it does not disappear at anything like the universal rate. They measure quite well-defined number for the second order loss coefficient. Here it is. If you evaluate the second order, the universal rate at 0 temperature, then you get something that's a factor of 4 different, roughly. But even if you put in the higher order, the higher partial waves, which are important, and the proper dependence of the S wave 1, you still get something that's a factor of more than 2 different. So this is going at half the rate that it would if it was universal loss. So what do we learn from that? What do we learn from the fact that this is not universal loss? Well, if we take those plots that I was showing you earlier and represent them a bit differently, what this shows is that this is the thermal average at a specific temperature, one of the temperatures of the experiment, 1.5 microkelvin. But it shows the loss at that temperature as a function of this loss parameter and the short-range phase. And on that diagram, the experimental number and its error bars limit you quite a lot to this. So the best fit is the solid black line, and the 1 sigma bounds on it are the curved black line. I wouldn't care to express that as numbers, but that's those are the ranges parameters that are emitted by the data. There's a tiny little thing here, but we won't worry too much about that. That's due to D-wave shape resonances, and it was conceivable at this stage, but was ruled out by the next stage. So this is telling us that it's clearly non-universal. Y is less than 0.4 everywhere here, but it's not at this point telling us anything about the short-range phase. So let's look at this in a little bit more detail. If we've got universal loss, the loss rate does depend on the short-range phase. What we can do is we can work out what the temperature dependence ought to be at each point along this fit. So for each value of delta, we can pick the values of y that are allowed for that delta, and we can work out what the temperature dependence would be for that. So that just says that. And that gives us this. So the various dashed lines and this solid blue line are all possible temperature dependencies, all of which go through the experimental point at 1.5 Kelvin, but are dramatically different, have dramatically different temperature dependencies. So you see this one here, actually, this is resonant, near resonant S-wave scattering. This one actually goes off. So the universal limit is here. We're not comparing with the universal limit. We're comparing with these 4 different colored lines. The solid blue is the best fit to this set of experimental points. And it has specific values of both this loss parameter and the phase. So the first point is that if you have the temperature dependence, that is very sensitive to the phase. So we can now refit those experimental data, putting in the higher temperature as well, higher and lower temperatures as well, and we end up with a much nicer, a much smaller area of y and delta that can fit the experiments. So we end up with y as about 25% plus or minus 0.03, and delta, which we've expressed as a multiple of pi, with a certain number. But if we express that as something more familiar, which is a scattering length, it tells us, gives us the first indication we've got of what the scattering length for one of these molecule-molecule collisions might be. Now, this is some kind of hokey, vague average scattering length, but nevertheless, it's telling us something about how close to resonant S-wave scattering we are for these collisions. So, what does this tell us, all in all, about the mechanism? First of all, the simple fact that it's second-order loss really quite strongly supports complex formation. Secondly, the original model of Myler et al. Doesn't work quantitatively. It predicts, the model would predict a rate that is the same as universal loss, and experimentally we get about half that, and that half is highly significant. One thing to note, I mentioned this when I was talking about the model to begin with, it doesn't actually matter what the number for the density of states is. This experiment is not giving us an effective density of states and telling us that the effective density of states is smaller than the Myler model. In other words, this result is not explained by what Thijs was talking about yesterday. But the rate does depend on this RRKM assumption, this assumption that the complex is behaving in some sense statistically, that formation of it's behaving statistically. And the fact that we're not getting a universal rate really tells us, we think, that RRKM statistical model of what the levels look like is breaking down. So really, only a fraction of the complexes that are formed are destroyed, and that is possible. But if all the complexes that are formed are destroyed, this tells us that the process of formation of the complexes is not statistical. And you can express that in various different ways. You could say that means that the mean width, for which there's a very well-defined expression in our RKM theory, is smaller than our RKM gives us. You could say that it means that the level pattern is more structured than random matrix theory. I think that's something that, yeah, I've kind of always thought it ought to be, because real Hamiltonians have structure. Real Hamiltonians are not random matrices, and so it seems to me to be an unexceptionable result that the real level pattern is more structured than random matrix theory. Or you could view it as saying that the closed channels, the channels that describe the complex, are not statistically coupled to the incoming channel. You can pick whichever of these languages you prefer as your way of thinking about it. Another way of thinking this that I quite like is that it could be that there's a geometric restriction on complex formation. In other words, that complex formation can occur when molecules collide at some subset of relative geometries, but not at other sets of relative geometries. I think that would have this effect of making the mean width smaller than predicted by our RKM theory. But one way or another, I do think that this is telling us that we have a lot more that we need to understand about these processes, and that the non-universality of this rate actually has important, well, not important consequences, but important interpretations in our understanding of this complex formation process. So that's pretty much the story, except to thank the people who did the work. First of all, I want to make it quite clear, all the experimental work here was done in the group of Simon Cornish. Simon is here. It was led by Phil Gregory in Simon's group. The guy who did most of the theory work that I've actually presented is Matthew Fry here, who's a great postdoc. But Thijs Carman was in my group for a while, a little bit before this specific project started, and we spent a lot of time talking about this, so I have a lot to thank Thijs for in my my general thinking about these projects. It's on archive. For some reason, my abstract isn't linked in the conference program, but I can easily send a copy of the abstract to anyone who wants it. So, thank you very much.
Thank you very much, Jeremy. Very interesting and quick question. Yeah, Concrete?
So I guess it's very interesting. So the rubidium cesium, I guess, case is quite different from sodium potassium in my opinion, because sodium potassium is a fermion, and that this two body and like a sticky, and then the third body that comes, that Tyson suggested that time scale would be 1 second. That was based on, I guess there's no Fermi suppression there, but the density was quite low. So would a third body that comes could still the time scale for this would be very different. Right?
Yeah, absolutely. But most of the stuff to do with the difference between bosons and fermions is in the quantum defect theory part of it, in the long range part. And that handles the bouncing off the long range potential. I think as far as the actual density of states is concerned of the complex, it doesn't make very much difference whether it makes some difference whether they're indistinguishable or not.
In terms of the third particle that comes, the time scale for that, is that very different?
Well, the third particle is a molecule colliding with a complex, so you don't have any fermion suppression at that stage.
I guess then there will be just density dependent.
Yeah, I think so.
Which
yeah.
I think in this case will be an order of magnitude faster, just from the density difference compared to the number you use.
I'm not quite sure. What do you mean by this case? Do you just mean RBCS as against other systems? Okay. But the potassium 39, sorry, potassium 40, I mean.
Right. So could that still be, I mean, I guess it may just be an order of magnitude which will knock it down to 100 milliseconds and still do slow.
We have estimates of this, and so we yesterday also gave the lifetimes that you would expect if there's only that loss. And this is sort of minutes for rubidium cesium. So I don't know if that.
I think what we're talking about is essentially independent of what it is that destroys the complex. You know, I mean, the modelling here applies whether a third body comes along and destroys it, or if a laser comes along and destroys it. Either way, what we're really attributing this non-universality to is the process of the formation of the complexes, not the process of the complexes falling apart. So we're seeing it as an entrance channel effect.
Yeah, one more question up there. Yeah, please. So,
can you comment on the effect of non-adiabatic interactions on these lifetimes?
So the various calculations of the lifetime so far, I mean, both John Bones and Tice's corrected version of it have no concept of diabatic or non-adiabatic in them whatsoever. They just assume that the entire energetically accessible phase space is sampled and that it's ergodic.
Because here, this is the way normally implemented in any QDT. You do this by a vibrational or rotational frame transformation in the asymptotic region.
Right. So what we've got a single incoming channel here, okay. And that single incoming channel. So it's two RBCS molecules in their ground, rotational, and everything else state, and they have a large C6 attractive C6 because of rotational dipole interactions. But it's a single channel model for the incoming part. So in that sense, there's no diabatic versus adiabatic.
Could you just briefly explain, you had curves which go above the universal limit. What do you think about this?
Okay, so in the absence of resonances, you can't have anything faster. So the universal limit is everything comes in, and some molecules come in, and everything that gets to short range is destroyed. If you have resonant S-wave scattering, then you have an amplification between the long-range wave function and the short-range wave function. And so, in a sense, the QDT is giving you an enhancement, and so you can have a greater probability. You can have a greater probability of loss than you would in the absence of that. So it's a resonance, and resonances can give you peaks above the average, and in a sense, the universal is just the average, without the possibility of resonant enhancement.
You mentioned that it is possible that your formation of conditional complex not totally statistical. Do you mean in the sense of statistical approach, which actually separates two regions totally when you look at collision starting from like an external reactant to the complex, and then looking independently looking after.
I think the separation between the short range and the long range is a different thing from the question of whether it's statistical or not. The question of whether it's statistical or not is really a question of the structure of the complexes at short range, or rather the Hamiltonian matrix for the complexes at short range. So if that matrix is completely unstructured in a statistical sense, in other words, it's given by random matrix theory and the Gaussian orthogonal ensemble, if we want to be specific, then you get the RRKM result. If that Hamiltonian is not random, if the eigenfunctions of it don't sample the whole of space, which is pretty much the same thing, then you will get something. Then you can't use RRKM. So it's non-statistical in the sense that the complexes don't sample the space ergodically.
One more quick question.
Yeah, I think I want to make a comment that is experiment can really contribute about this picture if you actually measure the resonance width, for example. Experiment like for example this kind of picture about the talk about lifetime of the complex. Well, I know that in atom molecule is certainly not quite right. I mean, atom molecule, so you have the rotational Fishbach resonances, and those resonances, the width is actually dependent on the anisotropy of the interaction.
I mean, I fully agree that what you'd like to be able to do is resolve these resonances and measure them, but the experiments that we have at the moment are so far away from being able to do that we kind of have to make the progress with the experiments that we've got. I do.
Actually, it's an experiment that will really tell us for sure, but theoretically, I know in the atom molecule, the lifetime is determined by the anisotropy. I mean, well, for the most part.
Yes, but that's in a perturbative regime, and a big so that's in a regime where you kind of have a bound state wave function that you have a zeroth order picture of, and you have a scattering wave function that you have a zeroth order picture of, and you can calculate a matrix element of a well-defined thing like the anisotropy between the two of them. There's a big question whether these systems are of that nature where you have a zeroth order picture and you can calculate matrix elements, or if they're in a different regime where the couplings are so strong that everything has virtually become statistical. And those are different ways of looking at it. And if they are statistical, you simply can't think about it in this nice small molecule picture that we're all familiar with and love. I think Theis's results suggesting that the density of states are not quite as high as we had feared are actually making us hope considerably more that we will be able to do these kind of precise measurements. If the densities were as high as John Bone had said, you know, it's going to be a long time before we can measure those. If the densities are much, much lower, maybe we will. We'd like to.
Okay, I think we have to move on. Thank you very much.
Thank you.
So next speaker is Lawrence Luke from John's group at Harvard, and he will tell us more about the nice little image you see on the cover of our program. And it's also going to be about calcium fluoride molecules. That's your USB.
Great. Yeah, that'll work. Thanks. Great. So first off, I want to thank the organizers for inviting me here today, and also thank them for organizing this wonderful workshop. Today I'll be telling you about very recent work in the Doyle group here at Harvard on laser-cooled calcium fluoride molecules trapped in optical tweezers. So for this audience, I don't have to give too much of a motivation, so it'll be very brief here. Essentially with molecules, because of their very rich internal structure, you can get many new features, which can be very useful for a lot of applications which we have already heard about, ranging from precision measurements to collisions and chemistry in the ultracold regime, to quantum simulation and quantum information. And for all these applications, we want to go to very low temperatures, and if possible, go to ultracold temperatures, because in this regime, we can, for example, trap these particles, hold on to them for long periods of time, and also control them fully, both in their internal degrees of freedom and also in their motional degrees of freedom. And we hope that, at least in the near future, we'll be able to gain the same amount of quantum control over molecules as we have with atoms. For example, seeing single particles in large quantum many-body systems, or even controlling every single particle using, for example, rearrangeable optical tweezer arrays. In the systems, one can envision building up large systems, one particle at a time, from the bottom up. So outline of today's talk, I'll tell you about how we load single molecules into optical tweezers, which are formed by tightly focused laser beams. Also how we detect them with high fidelity. I will also tell you about how this has enabled us to observe collisions, namely collisional losses between calcium fluoride molecules inside one of these traps. I will also tell you about very recent results from the past few weeks, where we can now take single calcium fluoride molecules in separate tweezer traps, merge them, and observe what happens. But before I get to tweezers, we first need cold molecules. As you have heard over the past 2 days, there are many ways in which we can make molecules, ranging from stark deceleration to cryofuges, to taking two ultracold atoms and coherently assembling them via stir wrap. Of course, I'll be talking about laser cooling of calcium fluoride. And in this approach, essentially, we follow what has been done in the past 2 decades, 2 or 3 decades with ultracold atoms. We use photons to slow and to cool these molecules down. And the practical starting point of these experiments is a magneto-optical trap, which is loaded from a source.
One of the key features of direct laser cooling is that it can be extendable to many classes of molecules, including complex polyatomic ones. Of course, this turns out to be a challenge, as we have heard from many speakers. We have to figure out how to plug all the leaks. I'll go rather quickly through this because we have already heard from Junyi and Dave DeMille and Nick and Mike Tarbit earlier on this problem. So simply by picking the right molecule, for example, calcium fluoride, we can suppress this vibrational branching. And relying on selection rules, we can also plug the leaks in rotation. But even after all of that, if one were to wanted to create a magneto-optical trap, there's still the problem of dark states, which we have heard about, and there are various methods that we can destabilize these dark states, including polarization switching, or maybe using more than one wavelength. There's another problem with molecules that rise from the large density of states. And the problem is that how do we start off in the states that we want? So one approach that we use is to start with a buffer gas source where molecules first thermalize with a buffer gas of helium-4 held at 1.5 Kelvin. And using this method, we can produce very bright and slow molecules in the states that we want, which is the electronic ground state, ground vibrational state, and the first few rotational states. So I won't go through all the details that lead up to the MOT, but putting together a buffer gas source, slowing of the beam, which is technically actually quite difficult, and all these ideas that I've mentioned, one can create a magneto-optical trap. As first demonstrated in Dave DeMille's group with strontium fluoride a few years back. And that really is was a milestone in laser cooling molecules because it provides us a practical starting point. And in the years that follow, magneto-optical trapping has been demonstrated in Mike Tarbit's group at Imperial here at Harvard, and also in Junyi's group for YO. So how do we get from a molecular MOT to optical tweezers? So as you have heard from Mike Tarbit, in these magneto-optical traps, by suitable intensity ramps, we can get fairly close to the Doppler limit. We can also have large number of molecules, 10 to the 4 to 10 to 5 molecules, at least large in the sense of loading a few optical tweezers. The main problem, however, is that the density of molecular MOTs are not high, at least compared to atomic MOTs. And one thing to remember is that optical tweezers are formed by focused beams of laser light, and we focus it down to near the diffraction limit, which means that they have a size on the order of microns. This means that the trapping volume typically is on the order of 10 micron cubed. On the other hand, a typical magneto-optical trap is on the scale of a millimeter. So I'll do the math for you, but if one were just trying to catch a molecule out of the MOT, in order to have near unity probability, one would need densities on the order of 10 to 11 molecules per cubic centimeter. So we're about 5 to 6 orders of magnitude away from the simple direct capture. So how do we bridge this large gap in density? So we rely on a very simple idea that can lead to very large enhancements in density. And this is to have laser cooling working also in the presence of a conservative trap. In this case, for us, it's an optical trap. So let me show you how this works. If you have a conservative trapping potential, if a particle starts outside the trap, it will essentially go through the trap because energy is conserved. However, in the presence of cooling, in the case where cooling actually works somewhere inside the trap, the particle can dissipate its energy and get stuck. And one can then start accumulating particles and thereby increase the density. Of course, there are a few requirements here. First off, the temperature that is achieved with cooling inside the trap has to be very low. Well, it has to be low compared to the trap depth. So either you have very deep traps or you have very low temperatures. More importantly, you need laser cooling to work inside these traps. Typically, we operate with traps that are on the order of a few hundred microkelvin. And if you convert it to frequency units, this is similar. This can be a few times the excited state line width. So in this regime, the actual states, ground states of the molecule can actually be significantly affected by the trapping potential, which can interfere with cooling. But at any rate, let's go ahead and look at how we can go to low temperatures, since practically there's with limited laser power, we can only make traps a certain depth. So as we've heard from Junyi, from Dave DeMille, and also from Mike, there are ways that we can get cold, much colder than the Doppler limit, which is 200 microkelvin in the case of calcium fluoride. You've already heard about gray molasses, where one can rely on a Sisyphus-like effect to go to low temperatures. So about a year back, we implemented the scheme, which was first demonstrated in the Imperial group. And what we found was that, in fact, we can make this gray molasses scheme work also inside these deep traps. And because of the effect that I just told you, we can vastly increase the density inside these optical traps by roughly a factor of 10. And as you have heard, there are ways that can get even colder compared to just simple gray molasses. We borrowed a page from Alkali Atoms, where we create coherent superpositions that are dark only when the molecule is slow. This was explained earlier, but the idea is, I'll go through this quickly. The idea is very simple and can be captured in a 3-level system. So here we have 2 ground states, A and B. And if you stare at it, you can see that this superposition state, A minus B, is actually dark to the light because the 2 arms, the 2 drives actually coherently interfere because of this minus sign. So as long as we make this dark condition dependent on the velocity, we can avoid recoil heating once the molecules get slow. And this can simply be achieved by sending in these 2 arms at different directions. So we implemented this, and in free space, this gets us rather cold by another factor of 10. But more importantly, this also works inside optical traps and gives us roughly another order of magnitude, getting to somewhere near 10 to the 8 when we first implemented this. So it gave you many different numbers. So just to put this on the map, since the first MOTS that were created with strontium fluoride, temperatures over the last 5 years, the temperatures have essentially gone down by roughly a factor of 1,000, well below the Doppler limit by now. And the densities have also gone up. And here, by implementing laser cooling, in combination with a conservative trapping potential, we can actually now push actually beyond 10 to the 10 per cubic centimeter. So the other thing that being able to laser cool inside optical traps buy you is that we can also detect molecules much more efficiently. So essentially by applying lambda cooling to optically trapped molecules and collecting the scattered fluorescence, which we call in short lambda imaging, we can collect many more photons than simple resonant excitation of the molecules. And when we first tried it out about half a year back, we were very encouraged because it seemed to suggest that it could make possible single-shot, non-destructive detection of single molecules inside an optical trap. So at that point, we realized that we actually had all the ingredients that were necessary to create single molecules and detect them inside optical tweezers. we had a way of overcoming the low densities in the Mach. And we also had the ability to see, or we should have the ability to see single molecules. So in the next few slides, I'll tell you specifically how we get from this large millimeter-sized Mach down into a micron trap. So we actually follow a two-step loading process where we go through an intermediate, relatively large optical trap. So first we take the Mach, that is about 1.5 millimeters. We apply lambda cooling to enhance the density inside this 40 micron 1064 optical trap. Then out of this relatively large trap, we try to pick out single molecules with even smaller tweezers that are about 2 microns. Specifically, in the loading step, we ramp down the intensity of the large optical trap while ramping up the tweezer trap. And very importantly, we have to leave the cooling light on so that the molecules have a chance to get stuck inside. So after some work and after many averages, we're very happy when we saw a first signal of molecules ending up where we expect them to be, or where the tweezer trap is. Of course, this is not quite enough. We want a little bit more. We don't just want molecules inside the tweezer trap. We want exactly either 0 or 1 molecule. There are many reasons for that, but one of the practical reasons is that if you know that the occupation is either 0 or 1, in a single shot, if you saw a bright spot, you don't have to think about what the occupation is. So how do you tell how many molecules are in the trap? We decided, before I tell you how we actually figure out how many molecules are in there, we decided that we'll just try out a way that could clean out multiple occupancies. Similar to work with atoms trapped in optical tweezers, we tried to extend the cooling light, which is near resonant, by a few milliseconds, in the hope that light-assisted collisions will clean out occupation numbers that are 2 or higher. So we applied this, and then we tried to figure out whether now we have single molecules. So to do that, we actually have to start looking at individual images. So the way we do this is that we take a region of interest in our image where the molecules are, and we sum up all the counts inside this region for every single realization of the experiment. Then we put this count, these counts, we put it on a histogram, or we make a histogram out of it. And when we do that, we see 2 features. One that is centered about 0, and then a secondary feature that is a little bit displaced. Now, this is not sufficient to tell you that you have single molecules. All it tells you is that sometimes you have nothing because you have a 0 peak. So to check whether we have single molecules, we varied the loading rate. So we kept reducing the initial number in the Mach. And we looked at how these histograms evolved. So when we reduce the loading rate, we find that the secondary feature decreased in amplitude. But importantly, the peak position did not move. And this actually tells us these are indeed single molecules. The reason being that if we had more than 1, as we reduce the loading rate, the mean would actually move lower. So knowing that we have single molecules, we went ahead to try to go more than, to try to scale up the system to more than 1 tweezer. And we do that simply by using a acousto-optical deflector to generate multiple traps. This device essentially deflects the beam based on what RF frequencies you put in. So we can have a single trap, and we'll see molecules trapped in one position. Or we can put 2 traps, and we can move them around even dynamically. Limited by power currently, we can get up to 5 traps. And with some improvements in the imaging, we can start seeing very resolved images of these single molecules. So shown here is an average image of 5 tweezer traps with single molecules. And to give you a sense of the signal to noise shown here is a single shot image, and you could already tell which traps are filled just from one shot. We can be more quantitative, and we can look at the histograms, and we can, and from the histograms we find that a few months back we could have a detection fidelity of around 93%, which we have improved now, as I will tell you in a little bit. So one can ask, is it possible to actually see collisions in these tweezer traps? I told you that we just extended this cooling light for a few milliseconds in the hopes that it would clean up multiple occupancies. So after we got the tweezers, we decided to try to see, resolve the dynamics of possible losses when we have more than one molecule. So just to slow things down a bit, we enlarged the trap to reduce the density. And we wanted to see whether 2 molecules inside a trap would decay faster than 1. And we need to slow down the dynamics because our imaging actually takes quite a bit of time. It takes on the order of tens of milliseconds, while collisions in principle could be much faster than that. So as you have heard in the previous talks, typically if you want to look for 2-body loss, you try to look for some sort of, well, second order loss. You want to look at non-exponential decay. Here we have a slightly different way of trying to tease out the signal. Instead of looking at this, we actually look at the histograms. And by waiting for long times, we can isolate what a single molecule plus zeros look like. And then we can go very far out in the tails where we know that there should be no signal coming from the single molecule feature. Then just by counting specifically in these high count regions, we can be sensitive to occupations that are more than 1. So here, to look at possible collisional loss, essentially we load the tweezer, which can have, for example, 0, 1, 2, 3, 4 molecules. We hold it for a variable of time, with and without cooling light, and see if we can observe decay. And when we did this, we find that whether we have the cooling light or on or off, multiple molecules always decay faster than single molecules, which can be whose lifetime can be obtained just by summing up in the region that corresponds to a single molecule. Of course, when we have near resonant light, the losses are about an order of magnitude faster. And assuming these are 2-body losses, we can actually extract the 2-body loss coefficient and also the inelastic loss cross-section. And these are in the 10 to the minus 10 and 10 to the minus 9 centimeters squared range. So looking at histograms, different regions in histograms is actually a little bit difficult. And also, just looking at the tails, we don't quite know whether these are single molecules. We don't know whether these are 2 molecules, 3 molecules, or 4 molecules. Where they contribute actually depends on the loss, and it's a little bit of a complicated problem. So why not make use of the new platform that we have, which are single molecules trapped in optical tweezers to study collisions? Namely, why not load 2 molecules in separate traps and then just merge them together and see how they go away in time? So before we start doing this, we have to improve our detection a little bit. So after some optimization, now we can get essentially 97% detection fidelity, which is sufficient for us to have non-destructive detection essentially at the 90% level. And we can check our non-destructive detection fidelity simply by first imaging the molecules and then re-imaging and comparing the two images. And currently, a large portion of this fidelity is actually just limited by collisions with background gas. So with this better detection, we moved on and tried to see whether we can detect non-destructively and also move the molecules after we have measured what their configuration is. So this is what I'll call detect and rearrange. So instead of 5 traps, I'll work with 3 traps here. So each trap can be filled or empty. So there are a total of 3 bits of information, and there are 8 possible configurations. Here, the circles mark the case when we have an occupied trap. For example, in this case shown, 101 would correspond to this row. So for this detect and rearrange test, what we do is that we first take a snapshot of these tweezers to identify which of the 8 configuration the system is in. For example, it's in this 101 configuration. And we'll implement a simple scheme where we just move all the molecules to the right. So essentially, we just shuffle everything here to the right. Of course, the movement depends on what configuration the system is in, so it depends on the first measurement. So in principle, in the ideal world, the result should look like this, where all particles start stacking up from the right, 1, 2, or 3, or 0. So we went into the lab after some optimization. We were happy to see that experimentally this does work out fairly well. And it might be hard to see, but this is actually experimental data. And the color scale here actually corresponds to something like 90%. And to read this table, essentially each row is conditioned upon the result of the first measurement. So great, we can non-destructively detect to check the occupation, and we can move them. So let's try merging 2 traps with single molecules to look for possible collisional losses. So here, again, we have 3 tweezers. And what we'll do now is that we'll keep the central tweezer fixed. And what we'll do is that we'll move the rightmost trap into the center trap. So we'll always merge to the center if it is filled. If it's not filled, then we'll move the left one into the center trap. And if both are filled, we'll always prefer the right. So in this experiment, essentially after the movement process, in the center row you will see either 0, 1s, or 2s, which is marked here in red. And now the next step is quite simple. We just wait and see whether the doubles go away. And of course we know when we have doubles because we have measured it first in the first step. So if there are collisional losses, we'll see that the doubles will go away quicker than the singles. There's a slight problem with this at this point, because if we were to detect the system, we wouldn't quite be able to tell 2s from 0s, because our imaging time is actually much longer than the light-assisted collisional lifetime. So we implement one more step where we just reverse this merge to the center step. We just split it back apart. And if we tune the traps such that they are balanced, then, for example, in this configuration of 020, there are 4 outcomes from the splitting process. It can be 002, 020, or 011. And 2 of these actually survived the detection procedure. So then we have a fairly simple scheme of measuring lifetimes of 2s. We know that they're 2s based on the first image, and we find out what fraction of those shots will give us 2 in the end, and how it varies as a function of hold time. So this is fairly preliminary data. So looking at all these possible channels where we can have 2, we do indeed see that this fraction decays as a function of this hold time. And to check that this is not due to technical heating during the movement process, we also have available in the data set the times when we only loaded 1 molecule, so we can look at the singles lifetime too from the same data. And we do see that the singles essentially have a very, very long lifetime compared to this tens millisecond time scale. And this is it's preliminary, and this actually is an updated plot from, it's about half an hour old. And this actually is a zoomed in region in between 0 to 80 milliseconds. And with that, I come to the summary and outlook. I have told you a bit about how we cool and load single molecules into optical tweezers and how we detect them with high fidelity. I've shown you some results beyond looking at 1 molecule, beyond single particle. I've shown you how by looking at different regions in the histogram, we can actually see collisional losses. And I've shown you some preliminary data on non-destructive imaging and rearrangement of tweezers and merging of tweezers to look for collisional losses. All these measurements are actually done in a single rotational state. It's in the first excited rotational state, but it is not hyperfine resolved. So that's something we would like to explore fairly soon. And by implementing optical pumping, just like what Mike Tarbert has shown, we should be able to isolate a single quantum state, and we can use microwaves to transfer into the absolute ground state to explore this, what happens there. All of the techniques that I have told you about in this talk are in principle extendable to other laser coolable molecules. And it's pointed out by Isaiah Wimberger and also by Ivan Kozyriev and collaborators. There are actually many molecules, including complex polyatomics and triatomics, where this is possible. We have already heard of some of this on triatomics from Nick earlier. And in general, with these new molecules, for example, triatomics, the new modes can lead to give you some favorable features. For example, bending modes in the triatomic can be particularly good for EDMs, or maybe for detection of dark matter. And going larger to, for example, symmetric top molecules, these new rotational modes about the symmetric top axis actually provide us doublets that can be very good for applications in quantum information processing. We just put out a paper on this together with Phelan, who's in the audience, and Ivan and John. And Phelan will be presenting a poster on this later today, so go talk to him if you're interested in this. I also want to advertise that there's ongoing work on triatomics in the Doyle group on laser cooling, both in CaOH and also YBOH. And there will be posters later in the day. With that, I come to my final slide. I want to acknowledge the fantastic team of people that have made all these results possible on the CAF experiment. Loic here, Yi Cheng, and also Sean. I think they're all in the audience. And there will be also a poster on CAF later. This is also a collaboration with Wolfgang Ketterle, Conquin Ni, and led by John, who's here, and probably up there. And with that, thank you for your attention.
It's awesome. Very nice results. Question, one or two? Please.
What about interactions during the splitting? They could bias the detection scheme. I guess you neglect them for now. You just treat they're not there, but that's
Yes. So.
not so clear, right?
Yes. So for strong interactions, this.
Interactions during the splitting process.
Interactions between the molecules?
Yeah. Well, when you go from
Just clarify.
Yeah, but when you go from two molecules to the split trap.
Yes.
I mean, I understand your hot and the dipole trap is not as confining, so interaction should be weak. But I think it's clear what you assume in the detection scheme is that interactions are non-existent. Because if there would be interactions, that would clearly bias the detection.
Yes. For example, in the case of very strongly or infinitely repulsive interactions, they would essentially always split into 1 and 1. So here in this case, we're assuming that the interactions are small compared to the temperature, which should be true in our case.
Probably anyway not a quantum. You probably just thermally activated hopping over the hydrogen.
Yes, and we also yeah. So there's also the issue of quantum statistics, which should not be a problem here because we are actually in many motional states, so we don't get 2002 for our bosonic molecules all the time.
And one more? Anya?
So you just mentioned that your motion is quantized, right, and you occupy many motional states. Does that affect the collision process?
We are essentially in the classical regime in terms of the motional states inside each tweezer trap. So the temperature inside the tweezer trap is actually much higher than what we can achieve with cooling in free space. It's on the order of tens of microkelvin to maybe a little bit above 100 microkelvin. So it's classical in that sense.
In your conditional experiment, did you extract the rate out? Or are you able to extract the rate or not?
So for the data that came from the histograms, we did extract two-body and elastic loss cross-section, but not for the latest data because we haven't measured the temperature or the density yet.
Okay, then move on. Thank you very much, Lawrence. Next speaker will be Binoy 2. Here from ITAMP, so we didn't have to travel very far.
Oh.
He gives a nice presentation about out of equilibrium quantum magnetism and thermalization in radio particles. So just roll to this. So you check the microphone.
For 2 minutes more actually.
Oh, here. This one.
Do you need that? Thank you very much, Chairman, for the introduction, and also I would like to thank the workshop organizers for giving me the opportunity to speak here. So from several talks, we have already heard about some very exciting new progresses in terms of cooling and controlling cold molecules, as well as their applications for quantum chemistry, precision measurement, and so on. Here, I would like to discuss some prospects from a many-body perspective. So using polar molecules for quantum simulation has drawn a lot of research interest in the past. Compared to other candidate platforms, polar molecules as a quantum simulator stand out due to several very nice features, such as the very strong interaction intrinsic to these systems, which allows for studying many-body physics and also for efficient quantum control. And also they have very rich internal levels, rotational, vibrational, hyperfine levels. And this also allows for flexible engineering of various quantum models. And so here is a plot taken from a previous review paper, which shows basically a landscape of using polar molecules for simulating quantum magnetism in lattices. And as you can see, in the pursuit of all these applications, a lot of effort in the past has been made to increase the filling fraction and also over the better control of the different complicated molecular structure. A demonstration for quantum simulation purposes has been shown and several years ago in an experiment done in JIRA using KRB molecules, which basically involves effective spin 1/2 system and with relatively low filling fraction. That's basically relatively this part of this landscape. Apart from that, most part of this landscape has remained unexplored experimentally. And it is also interesting to note in this figure that on the very right side part, there is this prospect for emulating magnetic dipoles using polar molecules, where we need to use a more complicated level structure. So the key ingredient for all these applications, as we all know, is the strong dipolar interaction enabled by the large electric dipole moment of the polar molecules. And so for typical experimental conditions, the lattice spacing allows for energy scale on the order of several kilohertz. So in the case for magnetic dipoles, basically we have a similar form of the dipolar interaction, except that now we have the magnetic dipole moment instead of the electric dipole moment. The magnetic dipole moment is roughly proportional to the total angular momentum of the atom. And so despite the fact that, generally speaking, the magnitude.
Is this one?
No?
It looks like. Could you tell?
Yes.
Okay. It's not very
Okay. Sorry about that. Well, so despite the fact that, generally speaking, the magnitude of the magnetic dipole interaction is much smaller than the electric dipole interaction. However, there are still several atomic species which allows for a considerable interaction energy scale, such as the chromium and the erbium. And especially in the past, there has been several experiments demonstrating the successful cooling down this atom species into quantum generacy. So in this talk, I would like to present you some recent findings that we made by studying these two experiments for chromium and erbium atoms respectively. So both of these two atom species, they have a large total angular momentum. For example, for the chromium, the ground state involves a total angular momentum of 3, which allows for 7 different Zeeman levels. And for the case of the fermionic species for erbium atoms, we have an extra nuclear spin, which doesn't really contribute to a stronger magnetic dipole interaction. However, it does give rise to enriched Zeeman level structure, which involves 20 different Zeeman levels. And in the experiment, typically what they do is that they have a sufficiently large magnetic field. And this means that in the dipole interactions, the total magnetization, non-conserving term is forbidden. And so now we have a relatively simplified dipole interaction form. And both of these experiments, they are done in 3D lattices. The typical lattice spacing allows for the bare dipole interaction on the order of 3 Hz and 0.3 Hz for chromium and erbium respectively. And also, we are in the regime of a relatively very high filling fraction for both of these species. So essentially, what we have is a long-range interacting many-body XXZ model. And the typical readout procedure in experiment is most conveniently done by measuring the spin population on the different Zeeman levels. And this can be done by simply doing the Stern-Gerlach separation. So with all this experimental capability, and essentially what we want to answer are particularly several questions, such as how does the dipole interaction manifest in the spin dynamics, and also how important is the effect of quantum correlations. And finally, do we gain anything now that we have actually a larger spin? So first of all, I would like to describe a little bit the theoretical approach that we use to study the quantum many-body physics in such systems. We would like to have an efficient numerical approach. This is because with such an approach, then we will be able to verify that the dynamics we observed from the experiment is really a result from the desired many-body Hamiltonian. And also with such approach, then we will also be able to characterize how much quantum coherence that we have in the experimental system. And we may even go one step further to identify the importance of the quantumness such that we may actually be able to use the experimental system for doing some task where the classical simulation is impossible. However, as we all know, it's generally a very difficult task to solve a quantum many-body problem. This is because of the increasingly large Hilbert space with the system size. In our case, we have actually a large spin S, and this means that we have even larger local Hilbert space, so that the total Hilbert space of the many-body system increases even faster. And on top of that, because we want to study the many-body physics, that also means that if we want to use some simple methods such as exact diagonalization, that will be simply inefficient. In experiment, typically the particle number is on the order of tens of thousands. And also because in experiment there is also this 3 dimension, and in principle the long-range character of the Doppler interactions also allows for a significant growth of entanglement. And this also means that the matrix product state-based methods are also non-applicable here. So the method that we actually use is based on phase space approach. So probably many of you are familiar already with this approach. This approach has already been applied for studying molecular collisions decades ago. And here we want to apply it for many-body setup. So essentially, the key idea of the phase space approach consists of the following procedures. First, we want to map our quantum Hilbert space to a phase space. For example, in quantum mechanically, what we have is a wave packet. And in the phase space, we can simply describe it in terms of like the 2 variables, x and p. And that also means that in the quantum operator, such as the x and p in the quantum mechanics now can be simply mapped into 2 real numbers in the phase space. And then because, as we know that in the quantum mechanics, there is the uncertainty relation, and so this can also be mapped into the phase space in terms of the initial distribution of the phase space variables. So then in order to obtain the quantum dynamics, we can simply, by solving the classical trajectory from each of these initial phase point, and then we do a statistical average over all these classical trajectories. So this method conventionally is called the truncated Wigner approximation, or TWA. And however, for our case, for the spin system, it is not, it doesn't work very well. So we need to improve it a little bit. So this is what we actually do. And so as we know that for our case, what do we have with the spin S system? This means that for describing local density matrix, we actually need n squared equals 2 plus 1 squared different elements. And so that means in the phase space, what we do to represent the local density matrix as actually we can just use generalized gamma matrices. And so despite like all this very messy mathematical form, but basically what you need to know is basically just that they are the generators of SUM group. And so now in the phase space, each spin is basically described by a generalized Blocher vector of d dimensions. And then we just do as a conventional TWA, that is, we just map to the phase space. And so to show you some idea of how this mapping is done, I will give you several examples. First of all, so for example, for the spin 1/2 system, and then the gamma matrix in this case actually is just a spin 1/2 angular momentum operators. And in the phase space, they can simply be described by the projection along the 3 different dimensions on a Bloch sphere. And for a spin 1 case, and then slightly non-trivial. Now we need 8 different components of the generalized Blocher vector. And so now, for example, in order to describe initial state in m equals 1, and then we in the phase space representation is in terms of all the possible values can be taken by these 8 different components of the generalized Blocher vectors. And then in the end, what we do is similar to the conventional TWA approach. Then we just basically, we can solve for the classical dynamics for each of the generalized polar vector, and then we can do a statistical average. It is also worth to point out that despite the simplicity of this method is actually capable of capturing the quantum correlations. This involves both the interspin correlation and the interspin correlation. So with the theoretical approach at hand, now we would like to apply it to study some real experimental systems. So the major part of our system is described by the dipole interaction. As we know, for a spin 1/2 system, if we prepare all the atoms in the same Zeeman state, the dipole exchange doesn't give rise to any population dynamics because this is the eigenstate of the Hamiltonian. However, the situation is different if now we have a larger spin system. And why is that? For example, if we just think of the dipole exchange, even though if all the atoms they are initially in the same Zeeman state, and one atom they can go up one Zeeman level while the other can go down one Zeeman level. And as a result, we will be able to see population dynamics. And basically, this results in a redistribution of the population along a synthetic dimension expanded by the Zeeman levels. As you already can see from this correlated nature of these hopping processes, this means that the quantum correlations can be generated during the spin dynamics. So this can be proved very easily in the experiment in such a procedure. So basically, you can just first prepare the atoms in the lowest the ground state of m equals minus 19½ and then you can use some RF tiles to to transfer the population into another MF state. And then you can just let the system to evolve under the dipole interaction. And after some time, we can measure the population distribution or different Zeeman levels. So here shows the comparison between actual experiment measurement using erbium atoms and the simulation result using the GDWA method that I just described. So you can see there is qualitatively, these two shows a very similar propagation along the synthetic dimension. We can also study the spin dynamics in a more quantitative way. So as you can see, so this figure plots the population on the three mostly populated Zeeman levels. The symbols are the experimental measurements, and it nicely agrees with the theoretical prediction coming from the dipole exchange interactions. And in addition, the experimental measured magnetization is also constant. This is consistent with the fact that the dipole exchange Hamiltonian does not change the total magnetization. In contrast, if we do not have quantum correlation in our system, this is what happens. And actually what we see is that there is much slower dynamics, and also the dynamics will be very sensitive to the initial conditions. For example, if initially we have all the populations can be perfectly transferred to a single Zeeman level, then what we see will be that there is basically just no population dynamics. And this can be understood in a very simple and intuitive way. This is basically because in the classical, if we have the classical dipoles, and the dipole exchange is nothing but this spin projection. And in this case, the initial state we have gives you a zero projection along transverse direction. So that means there is no effect from the dipole exchange interaction. So that means what we observed in experiment indeed is a quantum dynamics that come from the quantum correlations between the different atoms. And in addition, then what we can see here is that if we have only a nearest neighbor interaction, we also find a qualitatively different behavior between the numerical simulation and the experimental observation. And so this shows that the long-range character of the dipole interaction significantly affect the long-time dynamics observed in experiment. Given the fact that we have 20 different Zeeman levels that also provide us with the additional control knob. So basically, we can initialize our system in different Zeeman levels and then let the system evolve to watch the spin dynamics. So now you see, apart from the fact that we all see a very nice agreement between our numerical approach and the experimental observations, and so actually there is also a nice fact. So despite that, all this dynamics seems very different, but their shorter dynamics, they all shows a quadratic decay with time. And as a result, we can extract the initial decay rate. And so this shows the experimental result of this decay rate. And it shows that actually dynamics is faster when you initialize the spins in the Zeeman state is close to 0. And also, if we use this initial decay rate as some time scale to rescale our time axis, what we find is that all these different spin dynamics collapse onto a single one at a short time. And the fact that all these dynamics that collapse together also imply that it is independent of the inhomogeneous external magnetic field that is inevitably present in experiment. So the fact that there is such independence of the external magnetic field may seem surprising at first sight. However, it can also be understood in a very intuitive way. So basically, we have this dipole exchange process. If we consider a second-order perturbation theory, then what we can find is that the initial dynamic is simply determined by such a matrix element. And this matrix element will simply give rise to an initial rate, an analytic form of the initial rate. And so this tells you that the initial dynamics can be described by an effective interaction that is averaged over all the different pair of dipoles, and also there is an extra factor that's dependent on the initial state. So we plot this analytical prediction and compared it with the experimental result, and we find a very nice agreement. So this also demonstrates the fact that what the experimentally observed is the feature from the dipolar exchange interactions. In the last few minutes, I would like to describe another experiment where we can study thermalization in an ensemble of chromium atoms. So we have a large spin system, and we have multiple Zeeman levels. It turns out that we can also use the population on different Zeeman levels as a probe of thermalization. We have this Hamiltonian, which is long-range interacting, and also the experimental system is three-dimensional. And this means that generally we can expect that at a long time the thermalization will happen. And by this, then what we mean is that the long-time population on different Zeeman levels can be simply described by an effective thermal distribution. And apart from that, we have only two constraints to conserve the quantities. That's basically the energy and the magnetization. And with these two, then that will help us to determine the exact form of the thermal distribution. And with that obtained, then we can also analytically predict what is the long-time population of different Zeeman state. So this experiment is done with the chromium atoms, and basically what they do is similar to the Urban experiment. That is, we can quench our initial state to some spin coherent state with a tipping angle theta, and then we let the system evolve for a certain amount of time under the dipole interactions, and then we measure the populations on the different Zeeman levels. And so as you can see here, so here the symbols there, the experimental measurement of the population at a very long time. And we have this solid line that is the numerical simulation that obtained for a very long time. And also we have the dashed line, which shows the analytical prediction obtained from the thermal distribution. And you can see that all the three results, they agree nicely with each other. Not only confirms that indeed the experimental system thermalized to the expected thermal prediction, and also the fact that the GDWA method is capable even for capturing such long-time behavior. And it's also very interesting to look at how the system approach to thermalization. So this shows a full trajectory of the spin dynamics from the short time until the long time where they reach thermalization. And the dashed line shows the classical dynamics. So as you can see, well, the case for this codon correlation where we use the GDWA, so you can see very fast thermalization to steady state. However, for the classical dynamics, we see a qualitative difference in the sense that we still see a large oscillation. And this actually can be understood from the fact that classically, basically under the double interaction, each single spin basically precesses in an effective field caused by other dipoles. And as a result, this dynamics never damps. It's basically come from like the average over all different precession rate of the single dipoles. However, quantum mechanically, the thermalization happens differently, and because during the spin interactions, what happens is that different dipoles, they can also be correlated together. As a result, if we start from some product state at the beginning, and then because of the build of the quantum correlations and each single spin density matrix will become mixed state. And so here we can do this by looking at the single particle density matrix from our numerical simulations. And this plot shows the magnitude of the density matrix element for a single spin for different tipping angles and at different times. As you can see, for example, for a tipping angle of 0.5, and because we have initially a spin coherent state, we have a lot of populations for these off-diagonal elements. However, as time proceeds, because of the quantum correlations generated, and we see that only the diagonal part is dominantly populated, this also implies that now the system becomes a mixed state, and because of the buildup of the entanglement. And numerically, what we can do is that we can just calculate the second-range entropy for a subsystem of a chosen spin. And this, as you can see, these solid lines, they are the numerical predictions. And for each different dipping angles, they all reach some maximum allowed range entropy. Although this range entropy is not something that I can measure in an experiment, but they can measure something that is approximately similar. Basically, we can neglect the off-diagonal part of the single particle density matrix, and this is the quantity that is measurable in experiments, and it gives actually an upper bound, as shown by this red dashed line here. That gives an upper bound of the actual range entropy generated by during the dynamics. And this plot shows the comparison between the experiment result and the numerical simulations. The fact that we do see there is agreement between the numerical simulation and the experiment, and as well as the fact that we see an increase of the diagonal entropy, this supports the conjecture that we have a lot of entanglements built up during the spin dynamics. So to conclude, I will show you two experiment demonstrations as a quantum simulator of XXZ quantum magnetism. And so far, what we have done is to probe the features of this XXZ model in terms of the spin populations. However, it will also be interesting to look at other measurable observables, such as the quantum spin coherence and also the spin-spin correlations. And also, I've already demonstrated to you that we have a numerical approach, and which is capable of accounting for not only the large internal degrees of freedom and also the large system size as well as the quantum correlations. This numerical approach can be easily applied to other quantum spin systems, such as those designed for polar molecules. And also, it can be generalized to study some other cases, such as certain type of both Hubbard model and SU and spin models. And besides that, most of the cases that we considered here is for lattice with a very high freedom fraction. And in the future, it also will be interesting to look at the spin dynamics where we have a sort of an intermediate amount of disorder. And because for all the experiments that we have already done here is actually using the magnetic dipoles, and as we know that if we are able to use the polar molecules, and then the interaction energy scale is much stronger, this will also allow us to study something that is difficult to do with the magnetic dipoles, such as the interplay between this long-range Doppler interaction and motion. And because, as shown by some previous theoretical proposals, one can also use such as symmetrical total molecules to simulate magnetic dipoles. And in that case, it would also be interesting to look at if we can find some similar features. Finally, I would like to thank my collaborators. And so the experiment I done in Francesca Faleno's group for the urban atoms, and in Bruno Laura's group for the chromium atoms. And with this, I would also like to thank you all for your attention.
How much? Any questions? One or two? Please. So, how does all this dynamics depend on temperature? I mean, what are you assuming on temperature?
So in this case, basically we all have like a zero temperature state. You have a
in the spin sector, yes, but in the spin part I understand, but in the density sector not. So
Yeah, so we have
dynamics should depend also on temperature.
yeah, we have so for example in the chromium case, we have a unit feeding lattice, and the motion is basically forbidden in this case. So what we only need to consider.
What about random holes in there?
Yeah, exactly. That's for chromium. There is no random holes. It's a unit feeding. However, for the
If that's your simulation, yes. But the
no, in experiment, what actually, that's actually a good question, but this will involve some experiment details. Because like this boson, right, and so what they can do is actually first form a more insulator region.
Sure, but it's finite temperature, so there will be charge fluctuations.
Yeah, that's right. And but basically what they have is that they can also just remove the part where they have the doublings,
Right,
and then yeah, and so still they have a very large system, and eventually those fluctuations that you mentioned.
Wait, but when you remove the doublons, you still have holes, right? Then you have a lot of holes in there.
No. So what I was trying to say was that actually you still have a large enough system, right? And so in principle, yes, as you said, there could be some random holes, and that may actually play some role. And however, that is also like where our simulation can come in. Because theoretically, what we do is actually just use the unit feeding, and then we can compare that with the experiment measurement, and then we don't find any deviation to show there is a significant effect on the holes.
But I guess that's what I'm asking. How sensitive is this dynamics?
It's not sensitive.
It's
yeah.
not sensitive.
It's not sensitive.
So it's basically just next neighbor dynamics then.
No. It's not nearest neighbor dynamics as we confirmed that
But if it doesn't depend on the holes, if you can have many holes and you get the same signal.
The point is that they don't have many holes there, right? And so if you have a high enough density.
Wait. Sorry, slow.
Okay.
Maybe I'm too stupid to understand your point. I mean, you're saying that the spin dynamics does not depend on the number of holes, the whole dynamics.
If you have a lot of holes, then it will be dependent on that. And so that is kind of like you can imagine basically this makes a naive way of describing it, but it's like if you have some threshold of holes, right? And so then if you like beyond that threshold, then you'll find something that's very sensitive to the number of holes that you have, because as you said, so if you look at this simple theoretical prediction, the holes will also affect this average double interaction that you have. And this not only comes into the short-term dynamics, and that's predicted by this expression, but also the holes will also affect the long-term dynamics. And this is something that one can generally expect from this large difference between nearest neighbor dynamics and the average.
I guess what I'm asking, if we go back one slide where you did many curves, instrumental curves also. This one, yeah. So if I would have a system which has, I don't know, 30% holes, would the dynamics here look the same?
It will not be the same.
But not exactly, I understand. But will there be, I guess I'd like to be more quantitative, but okay.
Okay, so actually for this experiment, it's with urban, and we already have 30% of hole. And so then what
but this is the zero temperature calculation. So the experiment has 30% holes, and you're comparing to
in our simulations, we can we can account for that final temperature effect by
the line is zero temperature.
It's not, for this case it's not. It's not a zero temperature case. It already accounts for holes. Yeah, I guess maybe because I'm describing two different experiments, it may be a little bit confusing, but it's kind of out.
But how does the zero temperature? You for sure have done the zero temperature calculation. How does that look?
Basically, you for example, for here you basically do something like this.
Okay. One more? No? Then off we go to the poster session. Thank all the speakers again.